So in this design improvement, there were 3 other designs were proposed and worked upon in 2013 to 2019, and the PERC solar cell, and the PERT solar cell. This is called the passivated emitter rare contact, passivated emitter locally doped or totally diffuse contacts, and the designs are shown here. And this design, this is the PERC, and the dielectric layer is chosen as a Al2O3 or the silicon nitride, and with this efficiency about 25% were shown. And here typically it is shown that the number of grooves on a 156 by 156 mm solar cell were about 1130. So you can imagine how closely they were there, and this way the collection become more and the losses were lesser. Now another design came, and this is not yet in the production, but some companies are saying yes, they are going to have a production. I make a statement, maybe it can be. There is no contact on the top side. Only at the bottom side you have a contact, both positive and negative contact. It's a device you need 2 contacts at least. And in this design it is shown that you have a substrate, and again you have your emitter layer at the top completely and without any contact there, and at the bottom side you can have a N diffusion and P diffusion, alternate N, P and P, and this way you can take the contact selectively. So all the light you're coming on the surface of this cell is get absorbed. There is no loss, there is no aperture there. So it's a very much improvement, and it is shown for the N-type 26.7% efficiency here. So this is quite interesting and development taken place. Another solar cell that is called HIT solar cell, heterojunction intensive thin solar cell. Basically it is a combination of 2 technology, the silicon technology and the thin film technology. In the thin film, the amorphous silicon technology. Essentially in the amorphous silicon, you need to have a gases like silane and doped with boron doping or the phosphorus doping using phosphine as a gas or the diboron as a gas. So here you have a silicon surface, and then you have to deposit an intrinsic layer of amorphous silicon on the top of there the dope layer, and the back side also you can do. So it is a heterojunction, basically different band gap material, different material, it's a heterojunction. And here also improved efficiencies have been shown, and it is in the production line, 26.8%. These are all just recent development. And another technology, basically, I say it is at the laboratory level only. Now, we all know about the perovskite material. Lot of developments are taking place, but some stability issues are there, and that limits its commercialization. Perovskite is a ABX3 structure, and methyl ammonium lead iodide, normally the commonly used material for this perovskite. So you have a perovskite solar cell. Perovskite is made, you know that you have a substrate, normally the glass, then FTO layer, the transparent conducting oxide, the fluorine doped tin oxide, and then you have a ETL, normally
recording in progress.
TiO2 is used, and over that you have a perovskite layer, and then you have a your HTL, that is your whole conducting layer, spiro mainly used, and then you have a contact. So this is a solar cell configuration for your perovskite solar cell, and 25% is already shown there. And silicon solar cell, as I mentioned, whether it can be in the normal silicon, just a PN junction, or a heterojunction solar cell. Here this your schematic is shown for the heterojunction, silicon heterojunction solar cell, over there a cell of perovskite. The combination of these is a very interesting, but because of the limitation of perovskite, it is not commercialized yet, but about 30% in such kind of a structure is shown, and this way it crossed the efficiency of silicon 29% and above Shockley limit. But because of the choice of the 2 material in the tandem junction form, it is possible to achieve about 30% efficiency, and this I have shown here for 2 kind of a structure here. And the recent one, this is in the Germany, the 32.5%. Still, their structure design is not known. In a news media kind of in a PV magazine, these results were deflected there, but the exact design, what is design and other thing, it is not revealed yet. Very recent it is, just 1 or 2 months, I think March, beginning of the March this came into about the news. And other in the EPFL, it is in the Switzerland, there is a very important lab, particularly this is also a Gatzel solar cell was produced from this lab only, dye-synthesized solar cell, and they have also shown more than 30% efficiency, precisely 31.25% on the 1 centimeter by 1 centimeter square area. So these are some recent development, but these are not commercialized. It's very clear to us. It's all laboratory-based cell, and if it comes into the existence, definitely there will be a further cost reduction will come in the solar technology. Okay. Now I'll come to some NPL work. So we also motivated, yes, because in NPL we are working on perovskite solar cell, working on silicon solar cell. I'll show you some results of silicon solar cell, but before that, we first tried to see the this perovskite and silicon heterojunction solar cell. We did some simulation work, and you know that the solution-based process in NPL, we have also deposited 16% efficiency solar cell. My 4 colleagues from the group, they are working on it, and by the solution method process, but somehow its lifetime and other thing is not that much improving, because our motivation is not to improve the efficiency, to hunt for the efficiency. Our motivation is to how we can make it stable, because that is the demand of the researcher. If it is a stable with 20% efficiency with the cost-effective process, definitely it is going to be easier for the commercialization. And in this direction, we have done some work with the vacuum-based process. It is a non-conventional process, I mean to say, and work is going on. Maybe in near future, we will show some results with the vacuum-based perovskite material. As for the silicon solar cell, we are working on an industrial size wafer, that is 156 by 156. And this is also a new concept, the nanostructure base. Basically, if you see, these are some nanowires there. And we have made solar cell of this with 18% on bigger size, 156 by 156. Here our aim is to minimize the loss, and with our passivation layer and the texturing, we could able to lower the losses, reflection losses, I mean to say, lower than 2% or so. So with the combination of passivation and the texturing, some improvement we have seen in this solar cell. Though our efficiency is only 18%, but this is for the bigger size solar cell. And industries, these are looking for our unit processes. Basically, you know that in the solar cell, you have a number of processes. So industry can see our processes, like for texturing and your passivation. If they incorporate in their industrial line, may they get some improvement in their efficiency. And this is the design with the PERC. Other thing, we are working with a flexible silicon. The silicon, you know, that is a rigid. It is not a flexible. How you can make it flexible? By thinning the wafer. And when your wafer comes at a 50 micron or so, it start giving some flexibility. So as on date, the technology for the silicon solar cell is for the 180 to 200 micron. Some industries are working on 150 micron wafers. But if you reduce the thickness of the wafer, this way you can, your cost of the technology will definitely come down. So that is also a challenge, how we can minimize the uses of material in solar cell. So this is the one way you will use thinner wafer. And you can see some of our result here of the NPL, the flexi wafers, and there also we have made a solar cell. So this is basically at the top curve, if you see how this is the industrial wafers, it is shown data up to 21, and you can see how the thickness of the wafer is coming down. Other R&D, we are working, like I mentioned, for perovskite solar cell. Here, some of our data for flexible solar cell is given here for a smaller cell and with some larger modules. For perovskite solar cell, for organic solar cell also we are working. And one of my, I think, from my group, one student is going to present in this session only some of her work about the material for cell. And other thing, the combination of organic or inorganic, the solution-based process with silicon solar cell, there also we are working for making of a heterojunction solar cell. Now, so these are the some basically still researchers are looking for improvement in the efficiency, reduction in the cost. Challenges are there. It is not that we should not satisfied with the things, because we know that now we have a gigawatt installation. It is not that our job is done. Another challenge is there. These modules are installing large number of, you can see, it has its own life. Normally 25 years of a life. Where we will dispose of it? So it is a problem, big challenge for all of us. We are not realizing now, but definitely after 10 years we will have a problem, like electronic based or plastic based. Solar waste will be their problem. The NPL started thinking in this direction, and what this is just one slide to give you a magnitude of problem. I mean to say these are the top 5 countries and how much waste will be there by 2050 or so. This is for just that, and it is important. And you know that the solar, right now we have a linear economy basically from the quartz, that is the silicon or the sand. Your silicons are made, metallurgical grade silicon, then is purification, then wafering, then ingots, then wafering, then cell, another thing, finally installation, and no answer for that. So we need a circular economy. So that is why we need a recycling of it, and it's important there. So in NPL, this is, we feel, in India no one is working on in this direction. We just initiated few years back this work, and globally also very few. We have a collaboration with Australia, RMIT, and also with PTV Germany for this work. And we have developed a complete process, because NPL is a lab. We have shown for a small size module, and we could able to extract all the materials there. And you know that the cells are there, and for the module, the cells are sandwiched between your 2 layers of polymer that is called ethyl vinyl acetate. And then you have a glass and the back sheet, and in the cell you have a metals. 5 number of metals are there. You have a silver, aluminum, lead is also there. Now lead is replaced by tin. Some companies are doing it, but in the older module, though are already installed there, they have in those module leads are there. The tin, lead, copper are used as a step there. So that is so important. One should, when after its end of life, one should have a process for extracting these materials so that it can be reused. That is what the issue is, how efficient one can make. And here we have demonstrated after extraction of silicon and removing impurities, whether we can make again ingots, and we made an ingot of a small size, and so that we can make a solar cell out of it. And this is just in the thin film also we are working. You know that thin film solar cell are made on glass, TCO coated glass. So we could able to remove all the layers of the thin film solar cell and extracted the glass with TCO coating, and this can also be used for making of a solar cells. This is also a concern. In the perovskite solar cell, we all involved in the perovskite solar cell, but there lead is used. And you know lead is toxic. So we have to be very careful. Those who are working in lab, one should not throw your cells which are not working. We know that it is once measured or twice measured. Very soon it die. Basically hardly produce any power. So that's important. We should not throw in the dustbin. And if you are throwing it, just remove things properly. So this is also the process we have developed it, how you can remove this in the perovskite layer, and you can use this your TCO there. FTO, normally the FTO is used for this solar cell, because you have in the normal structure you have a ETL there. Okay, I think this with my I think time is also. So I made myself within half hour I should restrict myself. So I will conclude here. As I mentioned, crystalline silicon is a well-established technology. 95% market is captured by that only. But still there is a competition between newer and newer technology, and as on PERC and the heat solar cell, they have a competition. And I also don't know, I think majority of experts don't know which technology will overcome, because as you know that in the mobiles, changing is taking place very fast. In the solar cell design also changing is taking very fast in the same way. So that is the one thing. And secondly, the rapid development of low-cost processes is expected to move further. However, safe disposal of it is very important, the recycling. And third, in the emerging photovoltaic, we have to see whether the problem and the limitation of perovskite is, if it's overcome, definitely silicon and perovskite combination will be a great achievement for all the solar community, and particularly and plus all of us for sustainable development further. And CSR NPL is working in this direction, as I mentioned my work. And with this, I sincerely acknowledge my students, my colleagues from lab, and the funding agencies, CSR, MNRE, and DST. Thank you all.
So, any questions from the audience?
Online audience, please ask question or raise your hand. We'll unmute you.
Hi, yes. Yeah, see, tandem means definitely more than two it can be, but definitely two cell in a stack. So important is that the matching of first cell and the second cell, current matching is very important. Like if you have in one cell, current is more, and in the second cell, current is less. So you will get ultimately addition of the current of the first, the lowest current, and also from the second cell which are producing high current as such individually, but you will get add of that only. So that is important. In the tandem, if your question is that, if any kind of it, whether perovskite tandem, perovskite inorganic, organic, or perovskite silicon, also part of it, yes. Perovskite, yes. Whether in the organic form or inorganic form. Normally in the inorganic form, this is a popular material is your cesium tin iodide, in place of your methyl ammonium lead iodide. So lead is also removed, or the probability of more stability, because we know that organic is not that stable, the methyl ammonium. You can have a cesium or some other material. So it's an important way. People are started thinking in this direction also, started working in this. Yeah. Yes, please. Yes, we encounter that has to be very controlled normally, because we have seen cross sections there in the diffusion layer. If it is up to 5 micron or so, and diffusion has to be uniform. That is the one thing. And when you are going for thicker of the diffusion, normally it goes non-uniform. So you have a profile like this. So that poor the efficiency. Reduce the efficiency. Polycrystalline. We got the polycrystalline. Polycrystalline. purity was 99.945 precisely, if I have shown here. This is the what best we have got, 99.945. This is 99.945. And if you see our this XRD curve,
Yeah,
it
we are
shows-
able to grow only 2.5 to 25.4 of diameter of this.
exactly,
ingot.
because the limitation of our system.
Okay,
It is grown by SPS, spark plasma sintering.
okay, that is a limited one. Yeah, I
Limited
can
one.
understand that,
Yes.
SPS, yes. Right, nice.
Yeah.
Very nice presentation.
Thank
Dr.
you, thank
Sushil
you.
Kumar.
Okay.
So, very thanks, sir. And first of all, we apologize for the small technical break in between. And the Professor Sushil Kumar has covered from the deeply about the, thank you, sir. Deeply about the solar cells, about the efficiencies, different technologies of the solar cells, starting from the very beginning, and about the methods for minimizing the losses, about the thin films solar cell, which are something, some cost effectiveness.
Recording stopped.
And about the solar waste disposal also. So from the very beginning, from the development of the solar cell and to the disposal of the waste material. So sir has covered all the topics in a very short span of time. So for detailed, we can contact sir at NPL or through email or through visit to the lab. So very nice presentation, sir, and very thanks for you. So,
Thank you.
yeah, thank you, sir.
Now, I would like to request Professor Ranjana to felicitate Dr. Sushil Kumar with a memento and a certificate of appreciation.
Recording in progress.
ऐसे हो जाती है प्रोफाइल। हाँ, नहीं वो मेजर इशू, अगर वो बने तो फिर हम 25% बनाएं। वही तो। हाँ, तो उसके लिए हम लोग मतलब वही 17, 18, 19, 20, छोटे में 20 के आसपास पहुंच जाता है।
Recording in progress.
So for the next lecture, oral presentation, I welcome Dr. Sarplin. The topic of presentation will be influence of hydrophobic and hydrophilic environment on the emission of European films. So welcome, sir, and the time limit is 8 minutes. So, thank you.
So very good morning to all. Before proceed to my presentation, I sincerely thanks organizing committee for having me here and giving opportunity to be the part of this event. So today I will be talking about influence of hydrophobic and hydrophilic environment on the emission of European films. So we all know that the luminescence is a common phenomenon in our day-to-day life, and of course it affects by several things. We'll not go details in the applications because we know that it can be used in sensing, but everything depends on the quantum yield and how much is the quantum yield, that matters. However, it depends on several parameters. So it always a great concern about the fluorescence stability as well as their quantum yield. In case of emitting complexes, they are intrinsically hydrophilic, and therefore the property is liable to deteriorate in the most environment due to the ligand stability by water molecules. And this is what the challenge we had taken in, and then we proceed further. Though there are several processes for the preparation of films, we selected PEMU as an ideal material for making the multi-layer films. So let us understand what is meant by polyelectrolyte multi-layers, PEMU. These are ultra-thin films made using alternating layer by layer deposition of oppositely charged polyelectrolytes. And of course, this is what the figure shows here. This PEMU will have intrinsic as well as extrinsic size. And if you dip the substrate in these polymers alternately, you get the uniform films build up as shown here. Where these are the intrinsic sites where a pair of cations and anions will have repeat units interactions. However, in intrinsic sites, we will have polyelectrolyte charge is commonly compensated by the counterions. Whereas non-stoichiometry of plus and minus polymers require additional counterion to balance the polyelectrolyte excess. So why polyelectrolyte multilayers? Since they have their applications as cellular, it can be used as a chemical cellular interactions, coating applications, antimicrobial surfaces, as well as soft material. And as discussed that in biological or in physics it can be also used in as a computer chip. Similarly, having lanthanides as a light-emitting material due to its outstanding properties, trivalent lanthanum particularly, complexes are preferred for photon emitters. As shown here, it can be used in lighting, lasers, telecom, and it can also be used to form a complex material due to their long emissions as well as lifetime. So this is one of the example where polyelectrolyte multilayers were used to embed lanthanum, and the polyelectrolyte multilayer films were prepared. So these films were, since these are the hydrophilic films, the emission of the lanthanum was affected since the lanthanides are sensitive to water vapor. So we have asked ourselves a question saying that can we develop the hydrophobic environment for lanthanum-based optical material? Even if we develop that, what would be the effect of environment on the emission of the developed material? So we started with the synthesis of this ideal polymer, which we started with the commercial material and which was quaternized by fluoroalkyl chain. Further, the complete quaternization was conducted by alkyl chain, and it was confirmed by IR spectroscopy. So these are the structures of my material that I use for the polyelectrolyte multilayer fluorescent films. This is the europium complex. These are the polymers, cationic and anionic, and this is the P4VP which I synthesize. So from next time I will call this as a PDADMA, PSS and P4VP. And this is how we prepared the hydrophilic and hydrophobic films. So which was again used by layer by layer deposition method, oppositely charged polyelectrolyte. So here blue color and red color indicates that polyanions and polycations, and this is the process. I am not going to go in details due to the time limit. Since this, we prepared the films, the thickness was measured by ellipsometer, which was set as 70 angle, and we had approximately 95 nanometer thick for the hydrophilic system and the 47 nanometer thick for the hydrophobic system, which was standardized by our group that the 20-layer system is in case of PEMU is ideal. So this is what the material which we used, and the polymer films were prepared, followed by this equation where we have cation and anions having one negative chlorine, which is replaced by the dopant. So dopant is europium complex here. Further, it was again proved by this equation too. And so to answer the second question, if we have hydrophobic system, what would be the result? So we studied the photophysical properties. So this is the photophysical property absorption spectra of hydrophilic polymers. Hydrophilic means this polymer. And this is the absorption spectra of hydrophobic polymer, where we have this fluorine fluorine core is quaternized with the polymer. So as you can see here, the absorption spectra of this hydrophilic polymer is less compared to the hydrophobic polymer, which indicates that there might be some interesting properties when we look to the fluorescence. So photophysical study like emission was conducted for these three films. So this is what the European complex itself, this is what the polymer, hydrophilic polymer, and this is what the hydrophobic polymer that we prepared. And as you can see here, the emission itself, which is supported by the quantum yield, where you can see the European quantum yield, the drop cost film of European has 63% quantum yield. European with HCl has 24, whereas when European is in presence of hydrophilic polymer, the 22. However, when European complex is in presence of our hydrophilic polymer, the quantum yield increases gradually, which was again further confirmed by the lifetime, where the European complex, it behaves monoexponential whenever, like even if it is in the polymer. This is what the most important slide I would like to highlight here. So the red color indicates for hydrophilic polymers, and the blue color indicates for the hydrophobic polymer that we prepared. And we checked their, we exposed them into the water. The lab condition was 45%, relative humidity was 25 degrees Celsius, and the emission measurement was conducted under the humidity and adding the water. So we had these two films, one was hydrophilic and one was hydrophobic, so we were immersing them into the water. So this is what the shown here, where when we have this hydrophilic polymer, red color, as you can see, there is immediate quenching when you immerse into the water, whereas when we have hydrophobic polymer, if you immerse into the water, you don't see that much quenching. However, there is a recovery also we've seen, and this we conclude that the relative intensity after immersing of water is reduced, whereas in case of hydrophilic, whereas it's not affected in case of hydrophobic polymer. So this is what we'd like to conclude here, that we have prepared these polyelectrolyte multilayers, hydrophilic and hydrophobic polymers, oppositely charged polymers, and then we embedded the complex, and photophysical properties confirm that the 48% quantum yield in hydrophobic films indicates that the material can be used for further applications. So with this, I thanks my collaborators and NSUT, of course, for giving this, and conference committee for giving this opportunity. Thank you. I'll be happy to answer if you have any question.
So any question from the audience? Yeah.
Yes, please. Yeah. Yes, sir. So this is what the peak we were trying monitoring 640 and 472 for quaternization of carbon in case of pyridine ring. Basically 1600 will be the IR frequency of normal pyridine. When it binds to the, when it is quaternized, it will be converted, like the frequency will change. So this is how we monitor. So I haven't shown here higher spectrum, but then we see the shifting in the spectrum from 1600 to 1640 when it is quaternized. So we precipitated this polymer after quaternization in diethyl ether. Since the polymer is dissolved in diethyl ether, the unquaternized will go in diethyl ether, whereas quaternized polymers will precipitate in the diethyl ether. So you filter it, 1 hour will go out, and then polymer will precipitate out.
So let's.
And we did not go into that, since our target was just to embed in, check the hydrophobicity of that. But that is good question. It can be looked. Thank you.
So very thanks to the speaker.
Thank you.
And giving a good insight about the matter. And so welcome to the next speaker, Dr. Komal Bhardwaj, and the title of her presentation will be Understanding the Design of Pearlidamides for Effective Electron Transport Layer Materials in Organic Solar Cell Devices. So welcome, without wasting further time. So 8 minutes will be total time. Yeah.
Good morning, everyone. The topic of my presentation is understanding the design of perylene diamides for effective electron transport layer material in organic solar cell devices. So in this slide, first of all, I will explain about organic solar cell in brief. Organic solar cell is a device which uses organic electronic material as active layer. On the left side, here is a diagram of organic solar cell. It is a bulk heterojunction inverted geometry of organic solar cell in which we use a glass substrate onto which ITO is coated. ITO is indium titanium oxide, onto which electron transport layer material is spin coated, followed by the coating of an active layer. An active layer is a mixture of a donor and acceptor material. Here we generally use a donor as PTB7 and acceptor as PC71BM, followed by the coating of a whole transport layer and then silver as anode. Now I will explain the working of organic solar cell in brief. So when light falls on the active layer, the electron from the highest occupied molecular orbital of donor material get excited to its lowest unoccupied molecular orbital, forming an exciton. Exciton is a attractive whole electron pair, and then this exciton will get diffused at the interface of donor acceptor material, and then it will get dissociated there to form the separate charge carrier electron and hole. Then they travel towards their respective electrode to generate current. Now, why we are interested in organic solar cell? Because they have several advantages over inorganic solar cell. First of all, these are flexible, and then they possess large area deposition. They are semi-transparent in nature, so these can be used on windows as well. They have several colors. They are light in weight, and they are low in cost, their ease of fabrication, and they have low environmental impact. And lastly, they employ very cheap and easy tunable small organic molecules. Now, why I am doing this work? Because in organic solar cell, there are several layers like I told earlier, active layer, electron transport layer, and whole transport layer, but there is not much work on electron transport layer in organic counterpart. The importance of electron transport layer is that they act as a protective layer and compensates roughness. They also maintain oblique contact. They increases the efficiency of charge injection, which decreases the recombination, and they prevent chemical and photochemical reaction between the active layer and the cathode. So generally, we use organic ETLs are either fullerene derivatives or non-fullerene derivatives. The fullerene derivatives are either PC61BM or PC71BM, and the non-fullerene derivatives are either perylene diamide derivatives or naphthalene diamide derivatives or azazine derivatives, etc. So the objective of this work is to find out a non-fullerene derivative because they have several advantages over fullerene derivatives. They can be easily tuned for their band gap by substituting. They are easy to synthesize and purify, and most important, their batch-to-batch reproducibility. So the target of this work is to find a low-temperature solution processable, suitable transport layer material for stability and efficiency of organic solar cell. In my work, I am doing work on perylene diamide derivative. Why I selected perylene diamide derivative? Because they have high electron mobility through pi-pi stacking, and they can be easily modified for their HOMO and LUMO levels by substituting at core position or at imide position. Now, for synthesizing PDI derivative, we first derivatize PTCDA at either core position or at imide position. For core position, the reactions are multi-step, and for imide substitution, the reaction are single-step. And in case of imide substitution, the reaction yield is also high. So in my current work, I have synthesized 3 kinds of PDI derivatives in which PDI EDA is having a simple amine at imide position. In PDI DAP, the amine is branched, and also there is presence of secondary nitrogen, and in PDI PY there is aromatic amine at imide position. For the structural and optical properties, we used FTIR spectroscopy, mass spectrometry, and ultraviolet visible absorption spectroscopy. In case of ultraviolet visible absorption spectroscopy, the characteristic transition for 00 and 01 are observed at around 540 nanometer and 500 nanometer in all the 3 PDI. Now the main aim of this work is to find out what kind of material we can use as electron transport layer in organic solar cell. So we did cyclic voltammetry to evaluate the HOMO and LUMO level of these material. Now for an effective electron transport layer, its solubility is must, and second, the LUMO level should be in cooperation with the active layer. So for this, we first synthesize the quaternary salt of the PDI derivative synthesized. For synthesis of quaternary salt, the reaction of PDI material was done with methyl iodide. On formation of quaternary salt, the LUMO level get downshifted in comparison to their precursor. As you can see, in case of PDI EDAQ, the LUMO level is minus 4.18 electron volt, and in case of PDI EDA, it was minus 3.74 electron volt. In all the other cases also, the LUMO level is downshifted in comparison to their precursor material. Also, the solubility is enhanced in case of quaternary salt. Now, since we are using this material as electron transport layer, so the calculation of their electron mobility is must. So for that, we fabricated an electron-only devices, which is shown here, and the electron mobility is calculated using Mott-Gurney equation by using SCLC model. In SCLC model, the one electrode inject the required charge carrier, while the other electrode block the charge carrier of opposite polarity. In PDI EDAQ, we observed electron mobility of 5.7 into 10 to the power minus 4 centimeter square per volt per second. And in case of PDI PYQ, the electron mobility was low because there was presence of aromatic groups at the imide position, which disturbs the planarity of core. In case of PDI DAPQ, the mobility was found maximum 1.16 into 10 to the power minus 3 centimeter square per volt per second because of most appropriate LUMO level. Now finally, the devices were fabricated using them as electron transport layer, and on the right side the device structure is shown. In case of PDI DAPQ, the power conversion efficiency obtained was near to 7%, which was comparable to zinc oxide, which was comparable to the device fabricated using zinc oxide as electron transport layer. Zinc oxide is the most conventional material used as electron transport layer in organic solar cell, and here we target to eliminate zinc oxide by our organic material. Since zinc oxide has several drawbacks, like it has certain defects, and also in device fabrication, when we use zinc oxide, the annealing temperature required is around 250 degrees Celsius, which is very high, and sometimes glass cannot withstand this much of temperature. To further understand the device parameter, the device data was fitted into Breitenstein-Ribland model via nanohub, from which we calculated the shunt resistance and series resistance. The shunt resistance was found maximum in case of PDI DAPQ if we compared among PDI EDAQ, PDI PYQ, and PDI DAPQ. For a good organic solar cell, the shunt resistance should be maximum and series resistance should be low, since series resistance is originated from the contact resistance between the electrodes, and shunt resistance originates from the recombinations. Lastly, to conclude the work, in this work, we did a comparative study of different imide substituted parylene diamide as electron transport layer, and their electron mobility was calculated by using electron-only device. The most appropriate energy level of PDI derivative bearing aliphatic group result in their better PCE. The power conversion efficiency of around 7% was obtained with PDI DAPQ, which was comparable to the conventional material zinc oxide we use, and these results shows that aliphatic group which contain multiple nitrogen atom at imide position is better for highly conductive PDI derivative as ETL. Lastly, I would like to acknowledge Dr. Rachna Kumar, my supervisor, for her continuous support in this work, Director CSIR NPL and CSIR for funding. Thank you.
Any question from the audience? So let's thanks the speaker.
एक क्वेश्चन छोटा सा मेरी
Yeah.
क्वेरी है इससे, आपने जो बेटा वो दिखाया है साइक्लिक वोल्टामीटर का डाटा, उसमें आपने जो स्केल दिखाया करंट का, तो वो करंट आपकी मिली एम्पियर में है या मिली एम्पियर में या एम्पियर में, और दूसरा उसका आपने स्केल ही नहीं लिखा, कितना मिली एम्पियर या कितना एम्पियर है,
सर ये एम्पियर में है, वो स्केल इसलिए नहीं
ये
लिखा।
सीधा एम्पियर में है, एम्पियर में आती है करंट?
नहीं नहीं, मिली एम्पियर में आती है, बट जब हम उसको ड्रॉ करा था तो से
आपको स्केल तो होगा, मार्किंग तो होगी ना, कितने कितने
हाँ
मिली
जी।
एम्पियर, 10, 20, 30, 40।
So it's, yeah, sir. Sir have a one question, sir. Yeah.
yes sir, after 1 week also DAPQ was showing an efficiency of 6%. Initially it was yes sir. Yes sir. Sir, we are working on this factor also, that how we can improve the stability of the device. Yes sir.
So welcome to the next speaker of the session, Dr. Mohammad Ashif, and his presentation will be on the topic memory resistive devices for synaptic plasticity and learning behavior. So welcome, you will have 8 minutes.
So, thanks for giving me the opportunity to present my work. So, I'm Mohammad Asif, working under the supervision of Dr. Ashok Kumar from CSIR National Physical Laboratory. So, today I'm here to present about the memory resistive devices, means importance of the memory resistive devices. So, first, what is the memory resistive device? Basically, it is a kind of device in which the memory can be stored in the form of the resistance. So that's why we call it is a memory resistance. So the first concept of the memory resistance was given by the Leon Chiu in 1961. So basically it is a 4 fundamental passive elements like of others such as capacitors, inductors, and the resistor. So here we discuss about the memory resistive device for the synaptic plasticity and the learning behavior. So what is the memory? Basically, it is the object which is responsible for the receiving and the recording information is called the memory. So if we talk about the ancient time, means how the pupils was store their information until the electronic devices were not discovered. So at the ancient time, the pupils were store their information by using different unique things like notes, slate, and then bones and bronze utensils, bamboo slates, and then paper. So finally, in 1928, the IBM company was discovered the electronic device to store the information. So, and after that, there are some low-level memories came into the markets. So the mostly used, nowadays, the mostly use the flash random access memory for the memory storage. So, but it has some limitations. So that's due to these limitations, the researchers are trying to build a new kind of the memory storage device called as a resistive random access memory device. So memory is of the two type, that is the volatile and another one is the non-volatiles. But here we'll discuss about only on the non-volatile random access memory. So these are the different kind of the non-volatile random access memory, such as flash random access memory, magnetic random access memory. So but it has some limitations because it has the slow in the speed, less endurance, high operating energy, high retention, and some scaling issues. So due to these limitations, the researcher trying to build a new kind of the resistive random access memory, which is very fast, high endurance, low operating energy, highly reliable, and high scalability. So this means what comes after the flash, VBIT nano hops, the ReRAM will. So what is the resistive random access memory? Basically, it is that type of the phenomena in which the dielectric suddenly changes its resistance from one state to the another state, and that resistance state may be the high resistance state or the low resistance state, which can be denoted by the 0 and 1. So it is of the two types. One is the digital resistive switching and analog resistive switching. Means when the resistance switch abruptly from one state to the another state, called as a digital resistive switching. Means, and when we change that, when the resistance changes gradually from one state to the another, called as analog resistive switching. So this is the conduction mechanism about the resistive switching. Who are working on the metal oxide materials, means when we applied the field to the top and the bottom electrodes, so there is a movement of the oxygen ions and the oxygen vacancies. So due to these oxygen ions and oxygen vacancies, there is a formation of the thin conducting filament. So due to this conducting filament, the device switch from one state to the another state, and reversely when we reverse the polarity of the applied voltage, again these oxygen ions will recombine with the oxygen vacancies and annihilate the conducting filament, due to which the device again switch from the one state to the 0 state. So what are the motivations behind this resistive switching device? Why? Already there are several types of the non-volatile random access memories are available in the market. So and mostly, if we are talking about the NAND-based flash memory, which is mostly using in the today's time. So, this NAND flash memory, following the Moore's law, actually the Moore stated that the number of the transistors in the microchip double after every 2 years. So, but this law ends shortly, because in the left side of the picture, if you see how the density of the microchip increase after with time. So in this picture, we can see how the density of the microchip increase. Means when the researcher try to reduce the size of the microchip up to the 20 nanometer, it follows the Moore's law. But beyond 20 nanometer, there are some limitations, because it provides unavoidable generation of the heat when a large number of the silicon microelectronics is packed into the small area. And and there is a chances of the leakage of the current density. So due to these limitations, the ReRAM researcher try to build a ReRAM device. So the importance of the ReRAM is for the neuromorphic computing. What is the neuromorphic computing? Basically, it is an integrated circuit which can be used to mimic the human biological neural systems. So already there are neuromorphic computing is going into the market, because they have used the von Neumann bottleneck technology. Means when they developed roughly 80 years ago, it consumes that the energy consumption, pull the data from the main memory and then process the data and then send it back to the memory. So there is a bottleneck issues between the CPU and the main memory. So due to these limitations, the researcher trying to kind of build a new kind of the non-volatile random access memory, in which data can be stored in the same memory and then processed at the same place. So this is the our human biological neural system consists of a different neurons, means to consist of billions and trillions of the neurons and millions of the synapses. So here we talk about the two neurons, perisynaptic and postsynaptic neurons. So these, when the action potential is generated from the axons, and this send the signals to the outer membrane of the presynaptic neuron, and this here from the outer membrane of the presynaptic neuron, there is a neurotransmitter which can release from this membrane and reach to the neuroreceptor of the postsynaptic neurons. So basically, If we talk about the human biological neural system, means how the memory formed in our the human biological neural systems. Means how the old age peoples forget their memory with the age. Means with the gap between these two neurons, it will increase with the age. So that's why the old age peoples can forget their memory. So if the connection between the pre and the postsynaptic neuron is strong, then it means there is a chances of the strong memory. So, so this is the experimental details. I'm not going into the details. So this is the IV characteristics, and which can show there is a gap between these two resistance states. So here we can say that there is a memory formations. So our device showing the multi-level switching means for the high density data storage, there is a one possible way for the realization of the multi-level resistance state by controlling the intermediate resistance state. So here it can be decided by the current levels. So here there is a possible combination of that multi-bit data storage, that is 0, 0, 0, 1, 1, 0, and 1, 1 by applying these 400 exciton pulses. So this is the learning process, means how the human biological neural system learn the data. If we talk about the artificial synaptic device, means how we to learn the data to the artificial synaptic device. So here we try to apply the trained pulses of the same amplitude. So there is a non-linear change in the conductance, means when it gets to the saturation levels, means there is a long-term memories. And so this is the spike time dependence plasticity. We talk about how to learn the human neural network. For that, we have to validate the human learning rules. Hebbian learning rules. Basically, Hebbian learning rules means Hebbian stated that when the two neurons activate at the same time, so the synaptic weight should be large. So you can see here when delta t is very, very less, the synaptic weight is very high. So means it completely following the Hebbian learning rule. So finally, to test the accuracy of the device when we apply the artificial neural network, means when we applied a modified National Institute of Standard and Technology patterns to the artificial neural network, to the artificial synaptic device, means how much accurate it recognize the data, means how much it recognize this digit 2. So finally we obtain the accuracy of the artificial synaptic device is 73%. So this is the conduction mechanism, means there is a moment of the valency, selenium vacancies and selenium wines. So thanks for your attention.
Thank the speaker. Any question? One question only, if someone have. So I think we can proceed to the next lecture. Thank you very much. Yeah, fine. So welcome to the next lecture by Mr. Karan Garover on the topic effect of N719 didoping in triglycine sulfate single crystal, a potential non-linear optical materials. So yeah, start presenting.
Thank you, sir. A very good morning, everyone. I am Karan Garover from Department of Physics, NSUT. I am working under the supervision of Professor Ranjana Jha and Dr. Harsh Yadav. And I'm gonna speak on topic effect of N719 didoping in TGS single crystal, a potential non-linear optical material. So I will be discussing why I am preferring to work on the single crystals, what are the various methods for crystal growth. Then I will be talking about the TGS material, like its synthesis, then some of the characterization like the XRD, FTIR, PL and UV. Then I will be proceeding for the conclusions. So basically why I'm referring for the single crystals. If we talk like single crystals are free of the grain boundaries, so this is the best thing for the single crystals. So they provide us the quite homogeneity. Since they are free from the grain boundaries, so it is of definitely higher purities, because if we talk about the polycrystalline materials, they possess the grain boundaries, and these definitely do some defects there. So it is free from defects, so it improves the mechanical properties as well. And it also has some unique electronic properties like the charge carriers and all. And as a result, there are some better optical properties as well, as we can see from the UV graph further, that it is providing a very good transparency. So there are various methods for crystal growth, like it can be grown from the solution, water, melt, so there are various methods. The most commonly used methods are from the solution and the melt. From melt, we use basically the Czochralski technique. But the method that I've used is the solution growth technique, in which I've used the slow evaporation solution growth method. So the basic requirement for the slow evaporation solution growth method is the clear homogeneous solution. So we require the clear homogeneous solution, and we place it undisturbed so that the crystals can be formed. And to control the rate of the evaporation, we make some pinholes at the top of the beaker, and the pinholes can be made as per we need the evaporation rate. So talking about the triglycine sulfate, so TGS is the type of the ferroelectric and the piezoelectric crystal, and it has many unique properties. So it composed of the 3 molecules of glycine and 1 sulfate ion, and it belongs to the triglycine family of the crystals. So it is a ferroelectric material, which means it exhibits the spontaneous polarization, and it can be switched between 2 stable polarization by applying the external electric field. So due to this property, it has many applications in acoustic devices and many sensors as well. So this is a layout of the synthesis that we have used for the growth of the TGS crystal. Like we have used the glycine and the DI water, like 3 moles of glycine. Further, it was stirred till a clear solution was formed. To this, the H2SO4 acid in 1 molar percentage was added. And it was stirred until a clear homogeneous solution was formed. Further, it was filtered and put inside the water bath at 45 degrees Celsius. So after 7 days, we observed the crystals were formed. Similar technique was used for the N719 dye doping as well. And again, the same procedure was followed for the same. So this is the chemical reaction showing 3 moles of glycine and 1 of sulfuric acid to form the TGS. And these are the crystals. On the left side, we can see that there is a pure TGS crystal, and on the right side, there is the N719 dye-doped crystal. So powder XRD was done to see the structural analysis. So from the powder XRD data analysis, we found that the crystal has a monoclinic structure, and with space group to be P21. And the observed values were in good agreement with the JC-PDX data of the TGS. And from here, we can see that the doping of the N719 in TGS crystal had no significance on the XRD peaks position. But what we can see that here the intensity, there is a great change in the intensity, which may be attributed to the electronic change density in the crystallographic position of the TGS crystal. Further FTIR spectroscopy was also carried out. Again, we can see the minor shifts in the peaks position for the pure and the dye-doped crystal, and there were no additional vibrational bands which suggest the presence of the N719 additive to the TGS matrix. Also, we can see that no remarkable variation was observed in the FTIR spectra, which means that it does not affect the functional groups of the TGS crystal. Further, PL spectroscopy was also carried out, and we can see here that there is an increase in the peak intensity attributed for the dye-doping crystal. Later on, we carried out the UV visible spectroscopy as well, and it is said that basically a lower wavelength, cutoff wavelength for the transmittance analysis is preferred for the effective nonlinear optical applications, And here we can see that for the pure TGS, we are getting the cutoff at 254. But for doped crystal, here we are getting the cutoff at 249 nanometer, so which is again improving its properties. Further, torque plot was also plotted to check out its band gap values, which is 5.36 and 5.49 respectively for doped and pure TGS material. So conclusion is like we grow the single crystals of the pure and the dye doped TGS by the slow evaporation solution grow technique. And the dye effect of the dye on the structural and the optical properties were studied and investigated. And the changes were observed in the relative intensity of the peaks in the powder XRD, which confirmed the incorporation of the dye into the N709 into the TGS crystal. And the inducing lowering of the cutoff as a result of the dye doping suggests the use of these crystals in several optoelectronic applications. So these are the references, some of the references that I followed. Thank you.
Very thanks to the speaker. Any question? One question? Okay, it's fine, and thank you. So, one question. Yes.
एंड डोप उसका भी दिखाया आपने 79 डाई का। तो आपने मार्क नहीं की पीक्स जो रेड वाले में जो है, सिर्फ नीचे वाले में पीक मार्क की है, बाकी में
सेम पोजीशन पे ही लाइक कर रहा था। So
नहीं, तो चेंज है उसमें काफ़ी,
इंटेंसिटी
पीक्स में भी शिफ्ट है और उसमें भी चेंज है। एंड दूसरा जो आपने ट्रांसमिटेंस जो है उसमें देखा है, कितना % ट्रांसमिटेंस चेंज हो रहा है, वो आपने नहीं बात करी इसमें।
इन सर यूवी,
हाँ, नहीं, नो नो नो, जो आपने दिखाया था FTIR में ट्रांसमिटेंस दिखाया चेंज, कि उसका ट्रांसमिटेंस इतना है, इसका इतना है। यस, तो ओवरऑल चेंज इन द ट्रांसमिटेंट यू शुड शो, आपको डोप करने से। हाँ, देयर मस्ट बी ए चेंज इन द ट्रांसमिटेंस, बट हाउ मच % ट्रांसमिटेंस चेंज हैज टेकन प्लेस बाय डोपिंग दैट?
सर वो अलग से टेबल बनाया नहीं मैंने उसका।
ठीक है, ओके, गुड, फाइन।
Okay, so thanks all the audience and speakers for the session, and I think we can have a tea break of 5-10 minutes. Yeah, just a minute. Yeah.
So thank you, Professor Vinod Kumar, for chairing this session. So I request Ranjana ma'am to kindly give the certificate of appreciation to him. So there is also one more announcement that the participants who have the poster presentations, thank you. So the participants who have the poster presentations, they can place their posters on the respective boards are there on the right side. So you place your posters there for the afternoon session, means from the poster number 1 to 60. So then there will be discussion during the poster session time. So now we have the tea break, and after 10 minutes we will again assemble here. So in this, okay, 5 minutes because we are running late. So after tea, we will come back soon after 5 minutes. And next talk will be in this session will be Professor Rajesh Kumar from IB University, and in APJ 4, Professor Manish Kumar from JNU. So accordingly, we will join the respective sessions. Thank you.
Recording stopped.
Thank you. In this afternoon session, session 5A, we have one invited talk and 5 oral presentation. The invited talk will be delivered by Professor Rajesh Kumar from Indraprastha University, and the topic of his talk is nanoscale free value measurements of radiation induced modification in engineering polymers, or SSNDs by PALS, PALS. Now I invite Professor Kumar to please deliver his talk.
So thank you very much, sir. And first of all, thanks to the organizing committee and HOD of the Applied Physics Department, Professor Ranjana Jha, inviting me for delivering this talk. So today I will discuss some basic things. It's not a popular talk, it's just like a basic talk related to the MSc student or PhD students. So I think here the few students are MSc students. So today talk title is Nanoscale Free Volume Measurements of Radiation Induced Modification in Engineering Polymers, SSNTD by PALS. So this we will discuss about the engineering polymers, and SSNTD means solid state nuclear track detectors, and by PALS. So we have find out the free volume through this positron annihilation lifetime spectroscopy, means PALS. So this is my research group. So the few students have been completed and awarded the PhD degree, and the 5 students are working. And this is my research collaborators from the all over India, and some collaborators from the US also. So I did postdoc from the RPI New York, USA. So this is the our university main gate, and this is the night view of the Guru Gobind Singh Indraprastha University. And these are the some basic facility in our department. So we have the XRD facility and AFM facility and the same facility, and we have the NMR also and the micro Raman facility, and these are the some basic electrical measurement facility and DSC measurement and FTR, UV, like that. So we have sufficient facility in house. And recently I got this project from CRG. So now the project is open for calling for the applications. So those who are interested in this project, so it's related to the thin film and some gas sensing application of the 2D materials. So the last date is 15th May. So we are organizing this conference. How to that proceed? The 28th International Conference on Nuclear Tracks and Solids. It's in November 6 to 10. I cannot full screen. I cannot do the full screen. I do not know what is the reason. So conference date is 6 to 10 November. And this conference proceeding will be published in 2 prestigious journals, Journal of Electronic Materials, the impact factor 2.1, and second one, Journal of Radioanalytical and Nuclear Chemistry, the impact factor 1.8. And my research group is involved in the different field of the material science. So these are the summary of the work. So we are doing on some work on the thin films, and we are using the different techniques like RF sputtering and pulse laser deposition and atomic laser deposition and E-beam, etc., and chemical methods also. And second one, how to remove this first one. Okay.
and nanomaterials, synthesize the nanomaterial, nanocomposite materials, and nanowires, and polymers, nanocomposite polymers. And finally, we have after the synthesis, we can modify the ion beam modification of the materials, all materials, and take in the different applications also. And we are doing some application, especially mentioned in the above techniques, the gas sensing application, second thin film transistors, TFT, and lithium ion battery, and ion track filters, and environmental application through the SSNTD, solid state nuclear detectors. This is the summary of the work. So we are working on the zirconium oxide thin film. So we have deposited the zirconium oxide thin film by the RF sputtering. And the zirconium oxide found in three phases, the monoclinic, tetragonal, and cubic phases. And these are the some application of this zirconium oxide, like gemstones, enamels, and the oxygen sensors, CMOS, and zirconium crowns, high reflective mirrors. So these are the number of applications related to the zirconium oxides. So we have synthesized, first of all, we have synthesized or we have grown the thin films through this RF sputtering and modified by the ion beam, by the low energy as well as the high energy ion, and take the measurement by the, and or we can say the characterized by the different techniques. So we will discuss later on. And this is the schematic diagram of this. We are working on the MOS to 2D materials. So we have used the DC sputtering techniques, and we have used this this facility at IIT Roorkee, the Professor Ramesh Chandra's lab. So we have deposited the thin film in the different thickness, and we have modified, and we have taken the gas sensing measurements and other applications of this MOS2 materials. And this is the flow chart of the fabrication of the TFT after the sputtering of this MOS2 material. So these are the flow chart of this TFT. And second one in the right side, the schematic diagram of the sputtered MOS2 TFT. And after the growing this thin film on the silicon or SiO2, and we have modified the krypton ions by the low energy. And this is second one is the optical image of the pristine and modified thin films. And we have calculated the mobility through this equation. So we have calculated the number of parameters, pristine as well as the irradiate samples, mobility on-off ratio, transconductance, and subthreshold voltage like that. And another project we are doing on this tungsten oxide WO3 materials. So we have synthesized the WO3 nanomaterial by the co-precipitation method, and after the synthesis, we have annealing by the different temperatures. So these are the same image. You can see this, and another things, we have synthesized the hybrid nanocomposite materials by the drop casting methods, and we have taken the measurement by the gas sensing measurement, or second thing is the LPG sensors. So this paper already published in the Journal of Material Science and Materials in Electronics. It's a very good materials for the gas sensing application point of view. So these are the publications related to this material. And another projects in our lab, so we have synthesized the nanowires through this electrochemical methods. So in this case, we have synthesized the nanowires with the different pH value. So in this measurement, we found that the pH value at 1.7 is a good point for the growing the nanowires. You can see the F figures, pH 1.7. So it's a systematic nanowires through this electrochemical methods. And right one, so we have track H membrane. We are producing number of track H membrane through this ion beam modifications. So here in our India, we have no facility this type of creating the nanofilters in a systematic, but the GSI Darmstadt, Germany, we have taken the facility at GSI Darmstadt, Germany. So we have prepared these track filters. So it's a beautiful track. It's a size of 1 to 10 nanometer size. So we can enlarge the track size by the chemical etching methods also. If you want to more or thick nanowires, we can enlarge the size of these tracks. And another project I did this work at RPI, New York, USA. So we have made this anode material, lithium-ion batteries. So we made this anode by the red phosphorus in place of the graphites. So this the efficiency of the red phosphorus is the 7 times in comparison to the graphites. So, and second, one solid state hybrid fibrous supercapacitor produced by the dead and tube membrane ultrafiltration. So this project I did during my postdoc. So this paper already published in the Advanced Functional Materials. So it's a very good, we have taken the CNT and nanocomposite materials and some polymers. We did this work. It's a good candidate for the supercapacitors. Now the today talk is related to the polymers. So what are the polymers? So everybody is knowing the polymer definitions. So poly means many, mer means unit, many units. So this is the fundamental definition of the polymers. Polymers are very large molecules made when the 100 of monomers join together to form the long chain are called the polymers. So the polymers are divided in 2 parts, or we can say the types of the polymers, conducting polymers as well as the non-conducting polymers. But here, all plastic are polymers, but not all polymers are plastic. And the classification based on the source, so the polymers, natural polymers, semi-synthesis polymers, synthesis of the polymers, and the classification of polymers means branch-based polymers. So the linear polymer, branch chain polymers, and cross-linking chain polymers. So we will use in the pulse measurement the polymer chain or cross-linking polymers. Why use the polymers? So easy to process, and second, the cheap, lightweight, tough, flexible, and transparent in sometimes, not always, insulating generally. Generally, we are using the insulating polymers. And polymers are everywhere. So these are the some applications, and we are using the polymers in daily life also, food packaging, transportation, electronics, medical supplies, manufacturing goods. You can see that. Then construction work and the PCs. So everywhere we are using the polymers nowadays. So these are the ion beam facility were taken at different research centers. So we have used the facility in all over India and other places out of India. So Inter-University Accelerator Center, IUC New Delhi, is the prime institute for the ion beam accelerator facility. And second one is GSI Darmstadt, Germany. We have made a number of filters there. And third one is Joint Institute of Nuclear Research, JNR, Dubna, Russia. And VCC, Variable Energy Cyclotron Center, Calcutta, TIFR, and IOP. We have taken the facility at all places. So interaction of the radiation with matters. So these are the 3 types of the charged particles, electromagnetic radiation, and neutrons. Out of 3, we have used 2 charged particles as light charged particle, positron and electrons, and heavy charged particles, swift heavy ions in the different ions, carbon, oxygen, lithium, like charged particles. And second one is the electromagnetic radiation. So we have used the X-ray, not the, gamma rays, we have not used the X-ray. We have used the gamma radiation for modifying the materials. We'll discuss. Now the question is, now we are comparing with why we are using the gamma radiation and swift heavy ion radiation. So swift heavy ion interacts with the material in both ways. elastic as well as inelastic, whereas the gamma radiation interacts with the material only by the way of inelastic interaction. So this is the difference between the gamma radiation as well as the ion beam modifications. So this is the Swift heavy ion radiation facility at IUAC. So you can see then the left side, this is the chamber of the ion beam chamber, and this is the building of the IUAC second side. So first of all, when you are using the accelerator facility, you should maintain the vacuum in the chambers. So we have used the 10 to the power minus 6 torr was maintained in the target in the chambers, and we have taken the different fluence. Here I have taken this higher fluence, but you can start up to 10 to the power 6 to 10 to the power 13, 14 ions per centimeter square. So there is some limitations of the ions, and there are some limitations of the energy, there are some limitation of the ladders when we put the samples. So there is the size restriction of the samples. So the beam current was 0.5 PNA to 1 PNA. It's depend on the material to material. If you are taking the soft materials, like for example the polymers, so you have to take only the low current 0.5 PNA. If you are going beyond the 0.5 PNA, then polymers will burn out at the higher fluence. If you are taking the thin film, so you can go up to the 1 PNA and take the higher fluence also. And you can compare with this left side, the low energy ion beam facility, and the second side, right hand side, is the high energy facilities. So high energy and low energy means, low energy means KeV order, and high energy means the MeV range. So now the question is, what is the Swift heavy ions? So this is the simple definition. It's not a definition for the expert, just for the those who are doing the MSc students and PhD students, those who are interested in the ion beam modification of the material studies. So the Swift heavy ions are the specially form of the particle radiation for which electron stopping dominates over the nuclear stopping. So there are the particle accelerators to very high energies, typical to MeV to GeV at the high range. So have sufficient energy and mass to penetrate solid on a straight line. So straight line can create the tracks. Track means the hole, or we can say then the damage of the materials. And how to calculate the fluence? This is the simple formula. Those who are beginners and those who are the MSc students, they can see that how to calculate the time for the fluence, different fluence. So time is equal to ion fluence multiply the area of the samples. So the target size is restricted. So at IUSC, we have the size, maximum size 1.5 multiply 1.5 centimeter squares. We cannot go beyond of that size. So ion fluence multiply the area of the sample per centimeter square divided by the current PNA. We have taken the 0.5 PNA or to 1 PNA, depend on the material to materials. So current multiply 6.25 multiply 10 to the power 9 is a simple formula. And for example, let us take the ion fluence. If we require the ion fluence, the 10 to the power 11 ions per centimeter square, and current, suppose we have taken the 1 PNA, so area of the sample is 1 by 1 centimeter square. So just put the value in the above formula, then you will get the time of the fluence, 16.13 seconds. Okay. And second is, we have taken the gamma radiation facility at IUC also. So this is the gamma radiation chambers. So we have taken the dose of the 100 kilo gray to 250, 500 or up to 1250 kilo gray. So it's a high dose, or we can go up to 2000 kilo gray, but it will take some more time. Depend on the application, depend on your requirement. So simple that there was the definition of the Swift heavy ion. Here is the dose definitions, but how to calculate the dose. So the dose time, here also the calculating the time. Time is equal to 1 upon dose rate multiplied the required dose, how much you want to require the dose. So the dose rate is the 5.41 kilogram per hour. So this is the source of strength, and the required dose means 100 kilogram. Then just put the value, depend on the source strength. So the time is the 18 hours, 27 minutes, 49 seconds. So we can calculate very easy way through this formula, the gamma exposure dose. So polymer properties can be modified with the many ways as doping and other methods, variation of composition, mechanical stress, nanocomposites, and beautiful other technique is ion beam irradiations. With the different fluence, different energy, different charge, we can modify it, the properties accordingly to the applications. So the effectiveness of these modification produced in the polymers depend on the structure of the polymers or materials, and ion parameters like energy, fluence, mass, charge, and their nature of the target material itself. And third one, the detection and characterization of the defect, or means the free volume, or we can say the nanovoids in the polymeric material, are particular importance of the improved control of the material properties. So there are the number of techniques useful the defect investigation, none of which, however, can provide all information required to the definitive studies. So that's why we are using the different techniques or different characterization techniques. And this is the fundamental things, how to calculate the stopping energy or range of the ion in the metals. So it's depend on the target to target, depend on the energy of the ions. So we are using this TRIM software, so we can calculate the energy loss also. So here in the second one, so you can see this graph, the blue one and red one. So there are the two types of energy loss. Energy loss means in nuclear energy loss as well as the electronic energy loss. If you are taking the low energy ions, the nuclear energy loss is more. If you are taking the high energy, then electronic energy loss is more. So you can see this graph, energy versus the energy loss. So this is the same calculation. So we have taken the different polymers with the different thickness, macrofoil KGN and polycarbonate polymers, polyamide nylon 66, Cr39 dope. So the polyamide kept on as polypropylene. So we have used the different ion, different energy. First one is 100 MeV oxygen ion we have taken, and second one 70 MeV carbon ions and 50 MeV lithium ions. So here the projector range is in the last one. So this the microfoil Kg and 131.37, and second polymer nylon 6 and Cr39. So we can calculate through this software. So these are the general effects of the polymers by the radiation, gamma radiation as well as the ion beam radiations. So in wide range polymers, the following major modifications are observed as a result of the irradiation to the heavy ions. So means in previous slide we were talking about the types of the polymers, branch of the polymers, the cross-linking and the different. So cross-linking, first one, the modification is the cross-linking, the formation of lateral chemical bonds between the different polymer chains. And second one, degradation, so scissoring of the main polymer chain. And third one, gas liberation, and usually hydrogen, but sometimes including CH4, CO, and CO2, and other products of the side of the chain decompositions. And last one, we can measure the residual gas analyzing during the irradiation, which gas is residue or evaporate during the irradiation. So we can measure it. And these are some application of the radiation effects on polymeric materials. So we have different electronic energy and aerospace application, health physics, radiation dosimetry, particular biomedical application, bone tissues of engineering, and modified polymers, textile, mining, and construction industries, and magnetic tapes and discs. We are using the radiation-induced modification of these polymers and using these applications. And these are the some important application of the polymers under study. So we did lot of work in these polymers by the different characterizations, PMMA, PET, PADC, and PU polyurethane, and PEEK, and PTFE. So every polymers have the different applications and importance of the radiation in material science. So energy loss process responsible for the material modification and characterizations. So modification of the surface interfaces, structural transformation, modification of electrical and optical properties, and engineering of the electronic material and devices. But why this study? Why this study ion beam modification of materials or polymers? It is expected that different experimental studies will bring out the complementary aspects, and together with computer simulation and theoretical work will lead to the complete picture and may help developing the new polymers, new materials with precisely tailored properties of the scientific applications. That's why we are studying this. And these are the future prospects of the present studies. So this study can help the polymer scientists to have a better understanding of the polymer properties, which help them tailor these polymers according to their requirements so as to have better applicability in the material world. And our question is, every polymers have the void of the free volumes. So what is the free volume? So a small amount of unfilled volume is associated with the end of this polymer chain here, polymer chain. So this volume is called the free volume, and schematic diagram is represented here. So we are finding the size of this void is depend on the material to material. So we can modify this size free volume by this ion modifications. So the free volume modification mainly depend on the chain scission, chain cross-linking, and polymer structures, and ion energy, and ion species. The effect of the free volume modification upon the polymer properties. So these are the means free volume. What? So we can increase or we can decrease the ion conductivity depending on the free volume, polymerization, gas permeability, density of gradient, or structural properties. Why pulse? Why pulse is important? So positron can provide unique information on a wide variety of the problems in the condensed matter physics. It's not limited to the polymers. We can take this facility, the positron ionization lifetime spectroscopy, by the other materials also, the oxide materials and some nanocomposite materials like that. We can measure any void size through these techniques. Second one is the positron ionization can be applied in the field of the non-destructive. This technique is beautiful because of this destructive testing of the material, as the information is carried out of the material by the penetrating the annihilation radiation. So there is no effect of these radiations, the positron source. And third one is the equipment is not very expensive and is commercially available nowadays. But in India, there are the few places this type of facilities are available. The VCC Calcutta, SINP Calcutta, and then BRC, and some university also. And so we have taken this facility at the centers, Nucleus Science Institute of Nuclear Physics, Calcutta. So this is the electronic setup here in the left side, and right hand side, this is the detector. So we can put the samples between the two detectors. So we can measure the counts rates. So here we are measuring the 1 lakh counts. So it will take the time, more times. Okay. So this is the method posed on annihilation, so that this is the ion accelerators, ion beam, fall on this target polymer materials. So create the primary ionization and secondary ionization, and some create the delta rays also. And this is the polymers here, the blue colors, and this is the polymer change, and the gap between the polymer change is called the free volume. So we are finding this free volume size also. So these are the post-on annihilation spectroscopy have a unique combination of this techniques. So high detection sensitivity, near about 10 to about 16 per centimeter cube for vacancy open volume defects in any materials. So we cannot go to other except this TEM facility. And second, size estimation from the vacancies to the large open volume, moderate depth resolution, no need of the special sample preparation. It is just a simple preparation of the sample. Sample preservation, since techniques are inherently non-destructive, it can be easily integrated with the variety of complementary analysis techniques. So these are the family of the post-on annihilation lifetime spectroscopy, DBS, and angular correlation of annihilation radiations. So we are taking only the one facility, the pulse facility, and second one DBS, some cases. We have not used this angular correlation annihilation radiation because this facility is not available here. So this is the methods of the post-on annihilation. So we have the post-on source 22Na sodium source. So the post-on source intact or inside with the sample or materials. Then thermalization and diffusion of the sample. So diffusion length is the 100 nanometers. And annihilate with the electrons. So create the two gamma rays in opposite direction. So here we are measuring the time between the birth of the signal post-on here like this and the dead time of this. So we are measuring this delta T by this technique. And this is the formula tau 3. So here is the parapositronium and orthopositronium. They are the two types of the lifetime. So tau 3 is the longer times, or it's directly correlated the free volume size. So this is the formula. We can calculate the R and we can calculate the free volume size also. So this is the post-on parapositronium PPS and OPS. So you can see this. The size, the time period is 140 nanosecond, and the short time of this parapositronium is 125 picoseconds. So we are interested in only the OPS lifetime measurements. This is the method how to prepare the sample for the taking the measurement of the pulse. So you can see this is the simple stack of the foils, but the condition is the post-on source was sandwiched between the two identical samples material. The thickness must be sufficient, is greater than the 100 micrometer to absorb all the positons. Otherwise, the positon will out and annihilate the environment, so that your measurement will be wrong. So we should maintain the thickness is greater than 100 micrometers. Oh. So this is the spectra, the time period versus the counts. So we have collected the counts and we can draw, and we can separate the time tau 1, tau 2, tau 3. And these are the some intensity variation with this orthopositronium and parapositronium. And we are using the post-on source. Also the number of the post-on source are available, but depend on the half-life and depend on the beta decay of the maximum energies. So here we are using this 22 Na sodium. The half-life is 2.6 years and 90% beta decay. Okay, so we are using this source, but you can use other sources also, and it's very easily available. And we are taking the other facility like UV, FTR, XRD, and correlate with this free volume size. And so these are the some polymers and the ions, energy, fluence, and calculate the this energy loss. And these are the some sample thickness depend on the material to material, and 60 micrometer, 20 micrometer, and 125 micrometers, and maximum thickness is 250 micrometer. So this is an example is for the PALS, the polyamide nylon 66. So we have taken the measurement, the Poisson annihilation by the different fluence. So you can see this tau 3 orthoposition lifetime. Just 5 minutes, sir. Yes, sir. So lifetime, the pristine lifetime is 1.66. So you can compare with the higher fluence, means 5 multiplied 10 to 12 ions per centimeter square. So the lifetime is 1.65. So increasing the free volume size. So we have calculated the R and V and AV, fractional free volume, also calculated through this semi-empirical formula. And this data already published in the vacuum journal. So you can see this spectra also, channel number and counts. So you can see the different colors and the pristine to the higher fluence. So separate with the lifetime also. And this is the some XRD measurement, of same samples. So we can calculate the crystallite size here. So the pristine crystallite size is 13.32 angstrom, and higher fluence is the 14. So increasing the crystallite size after the ion beam radiations. And this is the UV visible. So we have calculated the band gap through this same samples. So you can see the pristine samples band gap 3.7 electron volt, and 3.63, 3.45, 3.07. So decreasing the band gap during, because the shift of absorptions is towards the visible region, attributed the formation of the conjugated system of bonds, increasing in the number of carbon atoms per conjunction length due to the cross linkings. Decreasing the band gap energy means the improve the conductivity. This is the FTR spectra. So here there is no more effect on ionization radiation, almost the same. There are some changes in the intensity of the peaks. And the same sample we were exposed by the gamma radiation. So the lifetime is pristine sample is the same, but at the higher, you can see the 100, the decreasing the lifetime, and 250 and decreasing, and suddenly the increasing the lifetime. So in case polymers, the overlapping of the tracks or chain seasoning, the increasing the lifetime at the higher dose. And you can see the free volume. The pristine free volume is 67, and higher doses the free volume is 71.33. So due to some time restrictions, so I am finishing just it. So these are the some XRD measurements. So we have calculated the crystallite size with the different doses. So in this case, gamma radiation dose also, the increasing the crystallite size. So this is the conclusion. So ionization radiation increasing in crystalline nature at the higher fluence by the pulse, and shift the position of the diffraction peaks, changes in the structure properties, improvement in the optical properties at higher fluence in the UV visible, and minor chemical changes in the FTR. But in the gamma exposure, in the increasing in crystalline nature at the lower and intermediate fluences, no shift in the diffraction peak by the XRD, and the increasing in crystalline nature at lower and highest dose through this XRD, minor chemical changes seen in the FTR, the similar. So the conclusion is that the effect of the shift heavy ion radiation was more than the gamma exposure. So we have taken the other samples, microfold kg, but here PMMA also. So we have calculated the same lifetime and other parameters. So we have taken the same results also after the gamma irradiation and ion beam irradiation. So the clear cut, you can see the clear cut difference between the ion beam as well as the gamma radiation in the same. So this is my research group, a small research group here. And these are my some publications in the last 1 year. And we are organizing this conference, how to, Manish जी, क्या नाम दुष्यंत जी, इसको थोड़ा इंक्रीज कर सकते हैं?
मैं ट्राई करता हूँ सर, ये थोड़ा zoomed है एक्स्ट्रा.
अच्छा,
ये बहुत बड़ा पोस्टर है
बस हो
सर.
गया, बस हो गया, हो गया. नहीं उसी को
इसी में
ठीक है,
दिखा.
नहीं, बस ठीक है. So we are organizing this conference, so you can note the date. The summation has been started, abstract submission has been started, and the last date is 31st July of the abstract submission. Yeah, definitely, yes, sir. Because NSUT is also the part of this conference. So we will modify the flyer also, yes. Yes, sir.
The co-organizer is NSUT,
Yes, yeah,
right?
yeah.
Okay. Thank you, Professor Rajesh Kumar ji. I hope the talk is very wonderful, must enjoyed by the most of the student, and he particularly emphasized on the fundamental aspect. And though it is a very complex technique, eye radiation for modification of a material, and he started with all the infrastructure techniques available at IP University, and I'm happy to know that you have an NMR now.
Yeah.
Yes, so
Yeah.
it's a very useful technique.
Yeah.
And starting from metal oxide and now to polymer. Polymer, that to a soft material, and ion irradiation on it for modification and making the changes in the volume aspects also. So it's a very important. So I hope the student will be motivated with your talk, and definitely they will submit abstract to this, your upcoming conference.
Yeah.
Now with this, maybe a few questions we can take up, because I know that we are running out of the time, uncontrolled time now. Anyway, maybe 1 or 2 questions quickly. Online, क्या बोल सकते हैं? No question. Okay. Okay. No question. Okay. Okay. So no question. Let us
Yeah.
thank a speaker.
Sir, कुछ पूछ रहे हैं.
Yes, sir.
Yeah.
Yeah.
Yeah. Mm-hmm. But depend on the free volume size. If you have the bigger free volume in any samples, it's correlate with the crystallite size also. ये time थोड़ा short पड़ गया ना, otherwise I will show the data related to the free volume correlated with the XRD crystallite size also. So, अच्छा.
Maybe
ठीक है.
during lunch time,
Yeah.
we can have a discussion. I have also a few questions I will ask during lunch time.
Sure.
Okay, okay. Let us thank, and organizers wish to facilitate Professor Kumar. Okay, now we will start oral presentation, and it's all online presentation. So first I would like to request Dr. Rekha Bhardwaj. Uh, She will be talking on structural and electrochemical properties of synthesized rhombohedral nickel sulfide nanoparticles. And you have 8-minute times, as it is fixed by the organizers. And we are also running out of time. If you can finish within the time. So please, you can start now. Dr.
Thank you,
Rekha
sir.
Bhardwaj, please.
Thank you, sir. Myself, Dr. Rekha Bhatwaj from Department of Applied Science, Bharatiya Vidyapeeth College of Engineer, and my presentation topic is structural and electrochemical properties of hydrothermally synthesized rhombohedral nickel sulfide nanoparticle.
Dr. Rekha, please.
Yes, ma'am.
Hello, can you fully screen your PPT?
Sure, sir.
Yeah,
ठीक है.
thank you.
As we know that our population is increasing day by day. Due to this, the consumption of fossil fuel are increases, which causes our several environmental problem. That is causes global warming, greenhouse effects, and etc. acid effect. Due to overcome of these problems, we have to find out the non-alternative of the non-renewable sources of energy, such as solar energy, wind, hydropower, geothermal energy, and hydrogen. These energy can be used by the help of nanostructures devices. First of all, we have discussed why nanostructures are used in energy devices. Because then at micro level, there are several different ones, such as energy devices technology, limited efficiency, high manufacturing cost, less flexibility, less energy payback time, and unstable time. And in nanostructures, we have several optical properties, tunable band gap, multiple exciton generation, surface reactivity, and flexibility. On the basis of nanostructure, we are divided into three categories: zero dimension, 1D, 2D, and 3D dimension. In zero dimension, a particle can be moved in all the directions, such as hollow nanoparticles, cluster, quantum dots. In case of one dimension, only particle can be growth in only one direction, such as nanowire. In two dimension, sheets and layered structures. The particle can move in 2D, and in 3D, these are the pillar-like structures we have observed. Why we are used nanostructure? These are the roles of nano and microstructures of energy conversion and storage devices. And the nanostructure particles have short diffusion length, large pore volume, homogeneous flow through pore structures, porous hierarchy, and large surface area, which are very helpful for the photoelectrics, fuel cells, dye-sensitive solar cells, and supercapacitor application, because it has small resistance, high storage device, high current density, and fast charge permeability. Why we are using metal sulfide energy storage devices? Because metal sulfides have controlled morphological size, composition, and other nano and microstructure. Metal sulfide has better electrical conductivity as compared to the oxide counterpart, and we have much more attention and more super comparable to metal sulfide. Why we are using nickel sulfide? Because nickel sulfide is one of the important class of the metal sulfide. Nickel sulfide has unique morphology such as caterpillar, cabbage, pompon, and etc. It has high theoretical capacity, high energy density, and high power density. Nickel sulfide exists in multiple phases such as beta NIS, NIS2, Ni3S2, Ni17, and S16. These are the different phases of nickel sulfide. Nickel sulfide has different phases of nickel sulfide and their structures. These are the various parameters which affect the electrochemical properties as well as the morphology of the nanostructure, such as surface, sulfur source, concentration of sulfur source, capping agent, temperatures, and solvents. These are the several applications which I have used as a nickel sulfide in energy storage device. Nickel sulfide used as a counter electrode in solar cell, and nickel sulfide as used in supercapacitor lithium-ion battery, and etc. These are the two parameters which I have studied in our lab. I have synthesized two nanoparticles by varying the temperature concentration. We are using the solvothermal method for the synthesis of beta NS nanoparticle, I am taking the ratio of ammonia and ethanol is to 1 is to 1 and ratio of nickel chloride and thiourea is 1 is to 3. And we are varying the temperature. For A1 sample, we are kept our samples at 160 degrees Celsius for 20 hours and we have found the nanoroid-like structure. In A2 sample, we have vary the temperature at 200 degrees Celsius for 20 hours and cluster bean-like structures we have observed, which are shown in the next slide. These are the XRD XRD graph of the synthesized samples. Red line indicates the XRD data of the synthesized sample clearly show that the synthesized samples are of the beta NS. The red lines indicates the refined portions. Blue line shows the difference between the refined data and the observed data, and the green line shows the Bragg's positions. These are the XRD refill refinement parameter which are observed from the refill refinement analysis. This is the Fourier transformation spectra which I observed, and these are not the impurities. These are the chemicals which are found and they are the synthesis material which are used during the chemical process or the synthesis process. These are the vibration band which are observed in the FTR spectra. ठीक है, OH vibration These are the FSM image which I observed. From the A1 sample, we have found that there are some nanoroid-like structure is used. In this method, you are taking the temperature at 160 degrees Celsius, and in the A2 sample, we have found the A2 is the nanocluster bean-like structures is observed. The size distributions of the cluster bean are diverse. They are not in individual group. And the surface. These are the several properties which I found from the nitrogen isotherm of the synthesized samples. The pore size which I have calculated from the plot and the VT plot which I have used for the surface probability. These are the pore size of the synthesized samples and the pore diameter and specific area of the synthesized sample A1 and A2. This is the UV reflectance spectroscopy graph of the synthesized sample A1 and A2. The energy band gap of the synthesized samples are 2.75 nanometer and 3.46 nanometer of the. This is the CV cyclic voltammetric studies of the curve from we have calculated from the biologic spectrum. These cyclic curve have been obtained from the different scan rate. At lower scan rate, we have got the maximum area because our electrode had maximum time. Because I have electrode have maximum time to pose the electrode and do the intercalation and deintercalation for processes. This is the slope of the scan rate and versus peak current, which process showed that the Faraday processes occurs, and the slope of 1 is equals to 1, indicate the capacitive behavior is dominating, and the charge storage mechanism diffusion control. This is the effect of scan rate. At lower scan rate, we have got the maximum areal capacitance values. Got the maximum areal capacity because we have the large enough time to control the pores of our structures. This is the various areal capacities of the at different scan rate. At higher, lower scan rate, we get maximum areal capacity of the synthesized sample. This is the eclectical cyclic stability of the curve at different scan rate. At 80, we have got maximum scan rate 83% in case of the A1 samples. This is the nucleus flow. With the help of the nucleus flows, we have find out the different structures such as our transformer resistance, impedance electrochemical, and this one. Black color show the raw data and the blue line show the fitted data. These are the parameters which are calculated from the nucleus plot with the help of JFIT. This is the Board plot. This is the frequency dependent plot which gives the value of the Board phase and the magnitude. The variation of the phase and frequency give the value, and it shows that our graph, the parameter which I have calculated from the nucleus plot. In the mid frequency region, it indicates that the phase angle of the sample 2, and phase angle is increases with increase in the frequency, which indicate that the sample A2 is less capacitive behavior. These are the conclusion. Beta NIS nanoparticle was successfully synthesized by hydrothermal route, and all the lattice parameters are calculated from the reticle refinement. Optical band gap of the beta NS nanoparticle is lower because of its temperature 2.75 electron volt, which are calculated by the UV diffuse reflectance spectroscopy curve. At lower temperature, we have found one-dimension nanorods were obtained, and one-dimension nanorod-like structures show superior electrocatalytic activity as compared to the sample A2 cluster bean-like structure due to large pore area and surface area of sample A1 as compared to sample A2. Sample A1 has high areal capacity as and show 83% cyclic stability in 1 million LiUH electrolyte over 1000 of cycle. This study show reaction temperature affect the electrocatalytic, optical and morphological synthesized beta NIS nanoparticle and manifested a reason for the synthesized single phase homovalent beta NIS carbonaceous free electrode for electrochemical devices. Thank you. Any questions?
Thank you, Dr. Rekha Bharadwaj. Thank you, Dr. Rekha Bharadwaj. Maybe we can have one question quickly. If no, let us clap for Dr. Rekha Bharadwaj for nice presentation. Now we move to the second oral presentation. Who is there? Hello? Yeah, the second talk will be by Dr. Lipsa Rani Karna, and she is from Department of Physics, Central University of Jharkhand, Ranchi. And the topic of the talk is structural and, enhanced performance of lead-free all-inorganic double perovskite photovoltaic. So let us welcome Dr. Lipsa Rani Karna. She will upload. Okay.
Am I audible, sir?
Yes, you are audible. Please move. You can start.
Okay, sir. Good afternoon to all. I am Lipsa Rani Karna from Department of Physics, Central University of Jharkhand, Ranchi, and my topic of presentation is enhanced performance of lead-free all-inorganic double perovskite photovoltaics. My outline includes introduction to perovskite solar cell, then the details about SCAPS-1D simulation tool. After that, I am going to discuss about the result and discussion, then conclusion, and at last the references. Introduction to perovskite solar cell. This is a type of solar cell where the observer material is a perovskite material with a chemical formula of ABX3, where A site can be replaced by a monovalent cation like cesium, methylammonium, formaldinium, and the B site can be replaced by lead, tin, like bivalent cation, and the X site can be replaced by the halogen ion. The perovskite solar cell has achieved a power conversion efficiency of 25.8% till date, but due to some disadvantages like the toxicity of lead present in the perovskite material and also the organic ion present in that material, the stability issues of organic ion, nowadays lead-free and all inorganic double perovskite comes into consideration, or recent research is based on lead-free and all inorganic double perovskite. The figure 1 shows the double perovskite crystal structure of chemical formula of A2BB prime X6, where A site here I consider two structure of perovskite solar cell. In one I replace A site by cesium ion, and other structure I replace A site by formaldinium ion. Then the B site can be replaced by bismuth ion, and the B prime site can be replaced by monovalent cation. Here I consider copper, and the X site is replaced by anion. Here I consider iodine. Figure 2 shows the different characteristics of perovskite material. different like high absorption coefficient, low trap state density, etc., for which it becomes a suitable material for photovoltaic application. Figure 3 shows our proposed device structure where we consider the TiO2 as ETA layer, that is the electron transport layer, and cesium and the reduced graphene oxide is taken as a STL layer, that is the whole transport layer. Also, here we compare the two structure, one is cesium based and other one is the fermadinium based device by a tool called CAPS1D, that is a solar cell capacitance simulator, which is helpful to estimate the photovoltaic performance of any device structure. Now comes to the details about the CAPS1D simulation. In this tool, the basic operation is operated under the 1000 watt per meter square illumination intensity and a device temperature of 300 Kelvin. And other parameters that are used here is shown in table 1. Also, this tool is operated based on the three semiconductor equations. The first one is the Poisson's equation, and other two are the continuity equation. Where from first one we can find the relationship between the electrostatic potential and the charge carrier present in that device, and the second and three equations gives us the relationship between the generation and regeneration of the charge carriers. Also, the charge transfer mechanism in the device is understood by these two equations, where Jn and Jp are the electron density, Dn and Dp are the diffusion constant, and mu n and mu p are the mobility of electron and holes. Then comes the result part from the simulation, and by seeing the figure 4a and b, we found that the cesium based double peroxide material gives better performance than the fermadinium based material. Also, figure 2 shows different photovoltaic parameters like open circuit voltage, AC value, and the field factor and PC. We found that the cesium based material shows better performance with a PC of 28.378%. At the cesium based material shows better efficiency. We consider cesium based device structure for our further analysis, where we vary the thickness of the absorber layer, SCL and ETL to see its effect on the photovoltaic parameters. By varying the thickness of this layer, we found that the optimum value of absorber layer, SCL layer, and ETL layer are 1000 nanometer, 800 nanometer, and 80 nanometer respectively. Then we vary the defect density of the absorber layer from figure 6a, A and B. We observe that by increasing the defect density, all the photovoltaic parameters decreases. We know that the defect density is associated with the recombination process going on that devices, which leads to the decrease in the lifetime of electron and holes. That leads to the decrement of all the photovoltaic parameters. Also, this process can be explained by these two equations, where SRS is the Shockley red Hall effect recombination, Shockley red Hall effect recombination. After that, we vary the series resistance and shunt resistance of the devices. From figure 7, we found that with low series resistance value and at high shunt resistance, we found the better photovoltaic performance of the devices. From figure 7a, we found that at zero series resistance, we found the maximum power conversion efficiency of the device. But as it is practically impossible, so we consider 0.2 ohm centimeter square as the series resistance value, and 10 to the power 6 ohm centimeter square for shunt resistance as the optimum value for our further calculations. These two equations show the relationship between the series resistance and shunt resistance of the device. Now we come to the final device structure, where final device performance. After all the simulation or the analysis, we found the optimized parameter for the thickness of observer layer, ETL and HTL layer, also for defect density and CT and sound resistance. And by taking all these optimized parameters, we simulate the final device structure, and we found that the final device structure gives a power conversion efficiency of 30.79%, 30.79%, and also the field factor of that final device structure is 82%. JSC value is 30.583 milliampere per centimeter square, and the VOC we found is 1.2 volt. Then comes the conclusion. From all the analysis and calculations, we found that the device structure with cesium based double perovskite structure, we found that the photovoltaic parameters are VOC of 1.226 volt, JSC of 30 milliampere per centimeter square, field factor of 82.096%, and the power conversion efficiency of 30.79%. Also, from the analysis, we found that the inorganic double perovskite solar cell, like the cesium one, gives better performance than the hybrid double perovskite solar cell, that is the permadinium based one. Also, these tools, these caps only help us to estimate the photovoltaic performance of a device before going to any experiment, which may helpful in experimental approach. These are my references. Thank you for your time.
Thank you, Dr. Lipsa. Maybe we can have one question.
Yes, sir.
As such, no question from audience. So, thank you, Dr. Lipsa, for nice presentation.
Thank you, sir.
Yeah.
Thank you.
Let us welcome next presenter, Dr. Anushahana Yadav. And
It's Anushansha Yadav.
Anusansaya, sorry, I am wrongly.
It's okay, sir, no problem.
Somehow I got in between somewhere. Anyway,
Gotcha.
yeah, you are going to talk on using SCAPS modeling to optimize the germanium-based perovskite solar cell. So again, we have a perovskite solar cell, and that too by the modeling SCAPS using. And she is from Department of Applied Physics, Delhi Technical University. So welcome you. You can start your presentation.
Thank you, sir, for having me. So, good afternoon, everyone. I am Nsut Yadav from the Department of Applied Physics, Delhi Technological University. I'm here to present my research topic, using SCAPS 1D modeling to optimize the germanium-based perovskite solar cell. So, in this presentation, we will first discuss about the introduction and the basics of the perovskite solar cells. After that, we will be discussing about the methodology and simulation. But before that, we will be discussing about the proposed structure and design of our solar cell. Then we will be discussing about the resulting results and discussion, and then the conclusion. Now, solar energy has emerged as a highly viable alternative to the energy derived from non-renewable sources in today's society, which is moving towards eco-friendly alternatives for everything. Perovskite solar cells, a third-generation solar cell, have gained prominence because of its low production cost, but lead-based perovskite solar cells have proved to be harmful for environment. So, tin and germanium-based perovskite solar cells gained a lot of popularity in today's time. In this paper, we have used a germanium-based perovskite solar cell, that is cesium germanium tribromide, and we have varied the thickness, defect density, and the temperature, and studied the effect of these variations using the SCAPS 1D simulation. So now discussing about the basic structure of a perovskite solar cell. As we can see here, we use TCO, that is transparent conducting oxide, as our top layer at top contact. Then we have HTL, which helps us to transport holes from the perovskite film to the electrode. Then we have a perovskite material. Its structure is ABX3, and it is used as an absorbing layer. After that, we use ETL, which helps in transporting electrons. And at the back contact, we use some metals. The commonly used metals are silver, aluminium, and gold. So now, moving to the structure of our proposed solar cell is that at TCO we have used FTO, which is fluoride, dogged tin oxide, and it is used as the TCO. Then we have C60 as our ETL layer, and cesium germanium tribromide as our absorbing layer, CuSCN as HPL layer, and Ag at that is silver at the back contact. This is the band diagram, energy band diagram of the optimized cell layers. So next, we have the methodology and simulation. So here we have used the software SCAPS 1D version 3.310. So the SCAPS action panel, when we run the SCAPS, we will encounter with this window. Here, with the second step is to define the problem. This can be done by just clicking on the set problem, and after we click on the set problem, we will get this window. Here we can design our structure as we want, and we can also change the parameters of each layer by just clicking on the layer and setting the parameters. Then our third step is to specify the working point, which is done from this part of the panel. That is, we can set the temperature, voltage, and series resistance, shunt resistance, and about the spectrum. Then after that, the fourth step is to what to calculate. Now here we can, as we can see, we can calculate IV curve, CV curve, CF curve, or QE. In our paper, we have calculated the IV curve and the quantum efficiency. The fifth stage is to start the calculation, which can be done from here. Calculate single shot, which will give you directly the graphs. Calculate batch, it will show you the influence of different parameters, and a recorder will show you the display the results of every calculation it has made. But in batch, it only shows the last measurement that it has made. Now the sixth step is to display the result. We can display our result from this section. So now we have the next is the results that we have found. So this is the result. These are the graphs that we have got from by varying the thickness of the absorber layer. So as we can see, JSC values first rises, then VOC slightly rises before becoming almost constant with the increasing thickness, and fill factor falls with the thickness, and efficiency increases. So this shows that the thickness of absorber layer, that is larger absorber layer, may absorb more photons, and as a result can provide excess charge carrier concentration at longer wavelengths, which facilitates the electron hole pair formation. Now, after this, we have obtained an optimized thickness at 600 nanometer. Then we have the graph for the variation of temperature. So here we have studied the effect of effect on different parameters due to variation in temperature. In this, as we see, the JAC first rises with the temperature, VOC, that is open circuit voltage, decreases with the increase in temperature, fill factor first increases and then decreases, and efficiency decreases with the increase in temperature. So this shows that higher temperature will have an impact on material properties like carrier concentration, band gap, and mobility of electron and hole, which will impair cell efficiency. So the optimized temperature that we have obtained is 305 Kelvin. So next is the effect of defect density on the various photovoltaic parameters. So here, as we can see, the short circuit current density, it is initially very almost constant, and then it decreases with the increase in defect density. Open circuit voltage initially increases and then it decreases. Fill factor decreases with the increase in defect density, and efficiency also decreases with the increase in defect density. Now, from this, we conclude that the efficiency is directly impacted by defect density, because as defects multiply, charge carriers diffusion lengths shorten, and recombination carriers accumulate in absorber layer. So Now, I would like to conclude my presentation by saying that we have used the SCAPS 1D simulator and obtained a power conversion efficiency of 11.35% with the structure of AgCuSCN CS GeVr3, that is cesium germanium tribromide material, C60 FeO at thickness of 600 nanometer, and the optimized temperature and defect density of the perovskite solar cell is 305 Kelvin and 10 to the power 13 centimeter per centimeter cube respectively. And when we compared this result with the literature, we have got that it showed an excellent result. Thank you.
Thank you, Anshansha Yadav, for finishing your talk in time. Maybe we can have one question. No question? Anyway, thank you. Once
you.
again, speaker, Dr. Anshansha. Let us clap for her.
Sir, just one more correction. I'm an MSc student. So,
Anyway, you are
yeah,
would be
not
doctor.
doctor.
Actually, see, for this na, it is very difficult to dig out whether you are a PhD student or a postdoctoral. So anyway.
No problem. Okay, thank you.
Okay, thank you. Let us welcome next speaker, Dr. Darshan Sharma ji, from Department of Physics, Department of Physics, Harish Chandra Postgraduate College, Varanasi. And she will be talking on, this is again on SCAPS 1D software, study of perovskite solar cell using SCAPS 1D. So, welcome Dr. Sharma. You can start your presentation.
Thank you. Thank you very much, sir, Dr. Sushil Kumar, sir. Am I audible, sir? Am I audible, sir?
Yes, you are audible. We can hear you very well. Please.
Okay, thank you. Thank you, sir. Good afternoon to all of you. As we are having a wonderful conference on hybrid mode, so I am lucky to present my topic. And previous two speakers, Dr. Lipsa Rani and Anshansha Yadav, has already described this software and perovskite solar cell introduction very well. So I will switch directly on my work. Before moving, I give you some data. Experimentally, perovskite solar cell have 25.8 efficiency as per NRE data. And theoretically, which material I have chosen, the study shows that 34% approximately theoretical efficiency has been achieved. So, my study is also based on tin-based perovskite solar cell. And tin-based perovskite solar cell has some shortcomings. Like they are having both SNI4 and SNO2 during commercialization of these type of solar cell. And they don't practice such purification. Also during deposition, there are oxygen exposure after deposition there is oxygen exposure which limited its performance. Also there are some too rapid crystallization, as well as there are not enough tin ions at B site. So I have chosen a perovskite material that have cesium tin germanium triiodide as a study material. And the device configuration was FTO, then ZNO as active layer, electron transporting layer, then light absorbing material, cesium tin germanium triiodide, then hole transporting layer, and then back contact as a gold. So I have optimized the thickness of these layers and band gap for ZNO, peroxide and full transporting layer. But I am not showing the data here. What I am showing here that whole transporting layer materials optimization. I have optimized this material using by 5 different material: copper SbS2, nickel oxide, Cu2O, and other two. So let's move on the results after simulation. So these are the results. As I have told you, in this type of peroxide material, only 34% maximum efficiency has been achieved, and we have achieved for NIO counter whole transporting layer 37% 0.23% efficiency, and this is because of this much of high VOC, open circuit voltage, as well as fill factor. Fill factor was almost similar for all the device, but VOC was highest in this case of whole transporting layer. This is JV curve and this is quantum efficiency curve, in which we can show easily here. Okay, blue color is not showing, it is behind the yellow color. So quantum efficiency, this one behind the yellow color. We are having highest quantum efficiency for NIO type of whole transporting layer. The variation of short circuit current density is given as per the material here, and VOC was the, obviously I have told you, highest for NIO case, and this is the for power conversion efficiency, not lowest, but range in 89 to 90%. In concluding remarks, I can say that tin-based hybrid perovskite solar cell we have optimized using ESCAPE software, and cesium tin germanium triiodide was the light absorbing material. Thickness was optimized and material for whole transporting layer was simulated to achieve the highest photovoltaic performance, and this we have achieved the record efficiency in theoretical simulation of perovskite solar cell of this type of perovskite, 37.30%. So I thank you to all of you for giving me this opportunity and listening patiently. If there are any questions, please, I welcome.
Thank you, Dr. Darshan, for giving this presentation and showing a very interesting result with your simulation.
Yes, sir.
Yeah, important is that it has to be realized with experiment also, because we have to make the solar cell as well with this much efficiency.
Yes.
So maybe we can have one question.
Yes.
There is no question. So let us thank Dr. Darshan for giving this time, and he has completed before time, rather I say, and we have saved few minutes. Thank you, Dr. Darshan, for this. Thank you very much. Now let us move to last speaker, Ms. Gauri, and she is from Department of Physics, Indira Gandhi University, Mirpur, Rewari, and she will be talking on effect of different parameters to develop efficient and sustainable earth battery system. It's a very important battery for us. So let us welcome Dr. Gauri for her
Good
talk.
afternoon, sir. Good afternoon, everyone. Thank you for having me. I'm Gauri Yadav, and I'm presenting my topic for effect of different parameters to develop efficient and sustainable earth battery system. First of all, we'll talk about need for alternative source of energy. Due to globalization and modernization, the demand for energy is increasing, and according to a survey of BP Statistical Review of World Energy 2020, approximately 84% of world's energy consumption needs are met from fossil fuels. And use of these fossil fuels also account to air pollution, soil pollution, water, human health, and entire ecosystem, and may cause non-communicable disease. Increase in population and technological advancement further add to depletion of limited fossil fuels. The decreasing availability of fuels and their detrimental nature necessitates search for renewable resources and alternative source of energy. As fossil fuels being the traditional source of energy, alternative source of energy used to replace or supplement fossil fuels, minimize fuel dependency, and alternative energy source such as solar energy, wind energy, hydrothermal energy, geothermal energy, etc. So, our Earth battery system is also a type of alternative source of energy as it gets charged in the presence of water or electrolyte naturally and does not require any external charging. So we are talking about Earth battery. An Earth battery system is a pair of dissimilar metal electrodes either buried in soil or immersed in water, producing telluric current using electrochemical reaction, which have two half cells, one at anode having low electron metal with low electron affinity, which undergoes oxidation and get positive charge and releases electrons, and another half cell on cathode side having high electron affinity metal, which undergoes reduction. And difference in the electron concentration cause potential difference, which generate current. Our problem statement is, as researchers are always in search of alternative source of energy other than conventional energy sources, which can reduce the greenhouse effect. Earth battery is also one of the type of alternative source, but a little work has been done in this direction due to insulating nature of soil and anode corrosion. Our work deals with investigation of earth battery system using different type of soil or compost as an ionic media and use of corrosion inhibitor for energy efficiency enhancement and stability. These are my objectives. First one is to study the effect of different type of soil and compost as ionic media in combination with different set of electrodes for earth battery system. And second one is to study the effect of antioxidants as additive in soil or compost ionic media based earth battery system. Our methodology is procurement and selection of electrodes and antioxidants. And then we are designing a cell for studying earth battery system and efficiency enhancement of the battery by selecting and optimizing the electrodes in tune with the chosen aqueous electrolytes. And we will use antioxidants or corrosion inhibitors for controlling the electrode corrosion by soil, compost, and electrolyte. Earth battery performance analysis are done by linear sweep voltammetry and electrochemical impedance spectroscopy using optimized electrode in selective soil, compost, ionic media in combination with suitable electrolyte. And these are my results. First of all, we have taken the first set. We have considered different set of electrodes. First set of electrodes we have considered here is copper and graphite. This is the LSV result for different type of soils. We have considered sandy soil, industrial soil, and black soil. These are my results. We can calculate VOC and ISC, which is open circuit voltage and short circuit current, which gives industrial compost as best among the three. And then we have taken EIS for different type of soil and compost, which shows least impedance in case of industrial compost, which tally the above result, which was in the case of LSC. Then we have considered another set of electrodes, which is steel 201 with graphite, and similar set of soil and compost, sandy soil, black soil, and industrial soil. Here also industrial compost gives the best result, best VOC and ISC, and similarly EIS has the least impedance in case of industrial compost, which tell you the previous result. We have also considered steel 301 and graphite. Their results has been compiled here. Here, if in case we see every set of electrodes, then industrial compost gives best result in every set of electrodes. And if in case we are looking for the best electrodes, it's steel 201 with graphite. Then we are talking about antioxidants on corrosion rates. So we have considered two set of electrodes, steel 201 with graphite electrodes. When we take additive as distilled water, in this case, so our corrosion rate is 0.76877 mm per year. But if in case we have added so it reduces almost to half and it becomes 0.36698 millimeter per year, which shows that has been reduced. Similarly, when we took copper and graphite set of electrodes, then this Staffel analysis has been done, and in case of distilled water as additive, our corrosion rate is 0.13378 millimeter per year. And when we add leaves extract as additive, am I audible? Sir, am I audible?
Yes, you are audible.
Okay. When we are taking leaves extract
Yes,
as
you are
additive,
audible,
its corrosion.
but your slide is not visible. It seems there was some net issue in between.
Oh, okay, sir. Okay, sir. Let me see.
Just check your slide. Your voice is
Okay, sir.
coming, but
Okay.
slide is not
Okay.
visible.
Okay, sir. Now am I audible?
You are audible as well as your slide is visible. Yes.
Oh, okay,
Yeah.
okay, okay, sir. Now, if in case we are taking additive as leaves extract, it reduces our corrosion rate from 0.13378, which is our reference in distilled water. It reduces to 0.11526 millimeter per year. This is our conclusion that LSC results reveal that open circuit voltage and short circuit current are found to be maximum in case of industrial compost or vermicompost based earth battery system comprising of steel 201 as anode and graphite as cathode in comparison to soil based earth battery system which has higher impedance. And in addition, corrosion studies was done using Tefl analysis which depicts lead extract as additive reduces the corrosion rate for vermicompost. These are my references. Thank you.
Yeah, thank you, Ms. Gauri, for nice presentation. And maybe we can have one question. No, there is no question. So once again, thank you, Gauri, for giving nice presentation and introducing us a very interesting your experimentation and the results. Thank you.
Thank you, sir.
Yeah, thank you. So with this, now we over with this session. Yeah, this is the indication. No, we should stop now. Yeah, yeah. So because it's a lunch time, I think we all are waiting eagerly to have a lunch, nice lunch. Yeah. Okay. Thank you. Thank you all.
At last, I would like to invite Professor Ranjana Jha to acknowledge Dr. Sushil Kumar for chairing this session 5. Now we'll have lunch time, then we'll have offline poster session till 3 p.m. So I request you all, please, to be gathered sharply at 3 p.m. Thank you.
So this is the announcement for all the online participants who will be going to present their posters online. So please be on time and join the Zoom. We are going for a lunch and then we will start here only, not in the APJ, but in the main room of the Zoom. So just join the room, no need to attend or no need to join any room. Just join the Zoom. And then you will see any host and he will guide you for the online poster presentation. Thank you very much.
Recording stopped.
हाँ नहीं पॉज किया है पॉज किया है अब यहाँ कुछ नहीं होना आज के दिन में एक है ना लंच के बाद पोस्टर्स के बाद एक है हाँ
presentation. Yeah. Is my
Sir, just 2 minutes. एक मिनट, वो फिर से unmute. Hello, I'm asking to unmute, sir. Can you please? Yeah.
unmuted?
Yeah, just 2 minutes, sir. Our session chair will invite you.
Okay. Is my slide is visible?
Yes, sir. Yes, sir.
Oh, fine. That's great.
You can put it on the slideshow.
Okay, fine.
Yes. So good afternoon, and I welcome all of you for this afternoon session. And for this session, the session chair is Professor Rajesh Kumar from GGIS Guru Govind Singh Indraprasth University, popularly known as the IP University Delhi. So he will chair the session. So I request Professor Rajesh Kumar to kindly chair the session, and then he will introduce Professor Tokir Ahmed, and the proceedings of this session will start. So Professor Rajesh, please.
So good afternoon, all in one, and welcome Professor Tokir Ahmed Sahab in this session. So we are starting the session 6. So in this session, we have the one invited talk and 5 oral presentation. So just I am reading out about the Professor Tokir Ahmed Sahab. Professor Tokir Ahmed is belongs to the Department of Chemistry, Jamia Millia Islamia University, Delhi. His area of interest is nanomaterials, nanocatalysis, organocatalysis, etc. And he is having the Teacher Excellence Award in 2022 and Maulana Azad Excellence Award. And he is the member of the many academic societies. So, for example, National Academy of Sciences, NASI, and he is the member of the scientific report Frontiers in the Chemistry and Materials Today proceeding, and he has published near about 273 papers in journals and 1 patent. So, welcome Professor Tokir Ahmed Sahab. Please deliver the talk.
Thank you, Professor Rajesh, the chairperson of this session, and I am thankful to the organizing committee, especially Professor Anurag, for inviting me for this conference. Good afternoon, everyone. After the lunch session, so today I am going to speak over the heterostructured nanomaterials for hydrogen production. So here, actually, for today's presentation, I have chosen the graphitic carbon nitride based hetero structures. So since actually the basic theme of the of my presentation is based on nanomaterials, so briefly I will speak over for some time about the basics of the nanomaterials or the nanoparticles. Basically, nanomaterials are very fine particles having grain size in the range of 1 to 100 nanometers. So actually, the typical size of any atom is around 1 to 2 angstrom. So therefore, in 1 nanometer dimension, we can arrange 3 to 5 atoms. So at this nanometric scale, the material shows some unusual properties because of the confinement of electrons, high surface area, and because of their small size, they are highly disordered electric and magnetic dipoles. And because of these unusual reasons, the nanomaterials could have find applications in electronic devices in the form of transistors, capacitors, in memory devices. You could say in your mobile phones, laptops, and other type of the devices. In the catalysis, today I am going to speak over the applications of the nanomaterials in catalysis. We are also doing to actually make the gas sensors, and of course in the energy storage devices. So actually, when we talk about the nanomaterials or the nanostructures, so these are of actually various types depending on their actually geometry, right? So it might be actually if the shape is spherical, it may be called as nanospheres or the nanoparticles.
It may be actually, if the shape is the rod shape, then it is called as the nanorods, nano-ovals, nano-triangulars, nano-cylinders. You can see over here, these are the nanotubes, these are nanowires, nanoneedles, these are bipods, tripods, and the tetrapods. And here you could see the core shell nanostructures. So actually, what happens in the actually, if one of the dimension is in the nano range, then these materials are called as the nanostructures. So when we actually reduce the size of the objects from micrometer to the nanometer, then what happens? The number of atoms at the surface, they will increase, and because of the actually surface energy is associated with the surface area, the surface area for a constant volume, it would actually increase. So this is the actually theoretical concept about the surface energy or the surface area in terms of the nanomaterials. So in the next slide, I am showing the mathematical concept how the surface area actually will increase. This is the experimental evidence that if you have the bigger cube, its covered area or the surface area is 6 square centimeter, and if you broken down this bigger cube into 8 more smaller cubes, then the covered area will increase to 12 square centimeter. And if you broke down these 8 cubes into 60 more smaller cubes, the area surface area will increase to 20 square centimeter. So how to calculate the actually, I am taking the mathematical example. How to calculate the covered area or the surface area of a cube. Actually, any cube having these 6 covered surfaces, and each surface is a square. And the area of a square is 2 into 2, means length into width. Right? So it will be 4. For if the edge length of the cube is 2 centimeter, now you have to multiply by number of surfaces, and that are 6. So therefore, the area of the cube having edge length of 2 centimeter, it will be 24 square centimeter. Now I am expecting the smaller cubes of edge length 1 centimeter. Then how many cubes I can expect actually of edge length 1 centimeter from 2 centimeter cube? So there are 8 number of cubes actually we can expect. And how to calculate the covered area or the surface area of these 8 cubes? You have to calculate the area of 1 cube, then you have to multiply by 8 number of cubes. And the area of 1 cube will be the area of a square into multiply by number of surfaces, that are 6. So 6 into 1 and then multiply by number of cubes, that is 8. So the total area of these cubes will be 48 square centimeter. So this is a practical example actually. When we reduce the size of a cube just from 2 centimeter to 1
Recording in
centimeter,
progress.
Hello, sir.
then its surface area will increase from 24
Hello, sir.
square centimeter to, yes.
Sir, your PPT is not on the slideshow mode. It's not in the full screen mode. Your
But it is in the full screen mode in my on my
so
laptop.
looks like then, because we cannot also see the moving slides here. Now we can see the moving slides, yes.
Okay.
But it is
Now
not
I am in the full mode.
still it is not here in the full mode, but it's okay. Now it's moving at least, so you can continue.
Now this is moving.
Can you move again to some other slide?
I am moving. I am moving.
No, it's not.
No?
moving. Maybe I think the slide size is too long. Maybe I think there are so many slides. I think, but maybe you can try to start your PPT again.
This is my. May I close it and then open?
Yes, yes, sir. Yes, sir.
Okay, fine. I am going to close it. And then, okay, fine, no problem.
Yeah, you can share your screen and then use the PPT on the share screen mode.
Yes, yes, yes. Now I'm sharing my screen. Should I share the whole screen or the PowerPoint?
You can share the PowerPoint only.
Only PowerPoint?
Yes.
Okay. So now I'm sharing the PowerPoint. Is it okay?
Can you move now?
Coming to the full mode and then moving.
But here it's not moving.
Fine?
Or maybe then
No, actually.
some problem here. Maybe you can.
No. Actually, I will share my screen. Whole
Yeah, you
screen.
can share your entire
Uh,
screen then.
yes.
Yeah, yeah.
Just a moment. Now I'm sharing the screen. Yeah. Now I have shared my screen. Now I'm opening my PPT again. Is my PPT is visible?
Yes, yes.
Full mode is visible.
Yes, yes.
Now I'm moving.
Right. Now it's everything is working now.
Perfect, actually, yeah.
Thank you.
Yes, thank you very much. Yeah. So actually, this was the mathematical concept how to actually just by reducing the edge length of a cube from 2 to 1 centimeter, the covered area will increase from 24 to 48 square centimeter. And when we work actually in for nanomaterials, then the edge length or the dimension actually we reduce generally 1,000 times. So now you can imagine actually the effective surface area. How much it will be, and because of the surface area actually you could see the changes in the application and other properties. So what happens actually when the size changes from millimeter to micrometer, then there is no change in the physical or chemical properties, but when size changes from micrometer to the nanometers, then most of the physical and the chemical laws changes, and because of the variation in the physical and chemical law, then their aspect properties like electronic, physical and the chemical properties changes, like the optical band gap will change, melting point will change. You can see the changes in the catalysis and as well as in the reactivity. And because of the high conductivity, high strength and high reactivity and high durability, because of the high surface area and because of their small size, they could be actually transported in the variety of the matrices. So the scientists or the researchers or the students, they have actually common platform where they can actually exchange their idea, that is called as the nanoscience and nanotechnology. So because of such kind of the properties, the nanotechnology is considered as the highly interdisciplinary area. So since actually today I'm going to speak over the catalysis part, nanocatalysis. So actually when we actually do nanocatalysis, then there are actually certain components of the nanocatalysis, like we can do the organic convergence reactions, organic transformation, we can do photocatalysis, electrocatalysis, photoelectrocatalysis. The basic objective behind nanocatalysis and its organic transformation, it actually depends, like if you are interested in the medicinal plants or the production of the industrially viable compounds or the environmental remediation, and the general mechanism about the catalysis. Actually the adsorption occur over the surface, and if the catalyst in the nano range, then it can actually absorb a large number of the reactant molecules, and when the adsorption occurs, the reaction would take place by the rearrangement of the electrons, and finally they would dissolve to form the final products. But today I am going to speak over the photocatalysis, electro and photoelectrocatalysis for hydrogen production. And actually in this slide, actually I have just shown that we have tried many metal oxide nanostructures that are structurally important, and we have applied these metal oxide nano materials for the various organic transformations like carbon-carbon coupling, hydrogenation, electrophilic cyclization, amination, and other oxidations. So, and we have actually a number of papers, and some papers are under communications on these this type of the concept. Now, I am coming to the actually water splitting. Basically, water splitting is a chemical phenomena, chemical approach where the water could be split into the hydrogen and the elemental oxygen. But the phenomena is not so easy. Actually, generally, we do the water splitting in presence of catalyst, and when it is exposed with light. And the normal available source, general available source for light is the sunlight. And if we see the solar spectrum of the sun, then you can see the visible light portion is the 46%. So our strategy is to develop the nanomaterials which are visible light active. Means if their optical band gap are in the visible region optical band gap is around 1.8 electron volt to around 3.2 electron volt. And we generally actually design these materials by making some chemical modifications, either by doping or by creating the heterostructures, so that actually we can tune their optical band gap into the visible region, so that actually these materials become active under visible light, and when they become active, I will show in my next of slides what is the mechanism actually, why we actually do this reaction. When they actually active, then actually they release electrons in the conduction band and holes will remain in the valence band. And actually, this type of the reaction you generally actually do by taking your advanced nanomaterial in water, and you have to add some amount of the sacrificial agent, and then if you expose with the light, generally we use the lamp, visible light source, and we do this reaction. So when we do this reaction, actually the first the photocatalyst can absorb the light and it can give the electrons, and actually our duty is to stabilize the electron hole pair structure, so that actually these electrons should remain free, so that actually it can reduce H plus into hydrogen gas. And this is the actually reaction setup that I am doing in my research lab at Jamia, where actually we can do the water splitting reaction. Why we are interested in actually hydrogen? Basically, actually hydrogen is considered as the green energy, and actually the worldwide you could see the energy crisis because of the overpopulation, overconsumption, poor infrastructure, and number of reasons are there. So actually, and it is a well-known fact that the Earth will finish very soon. So the world is looking for the alternate source of energy, and the hydrogen is considered as the clean and the green fuel because it has zero impact over the environment, because it is environmental friendly. And when hydrogen is consumed into the fuel cell, then it produces only water, electricity and heat, and it is carbon free and highly abundant. So generally we produce hydrogen by using photocatalysis, electrocatalysis, or the photoelectrocatalysis, and collectively all these methodology are called as the overall water splitting, and these overall water splitting are considered as the most prominent methodology of what is splitting of water to produce economical hydrogen to resolve the energy crisis issues. And this is the photocatalysis, and this is the photoelectrocatalysis. Actually, electrocatalysis is the simplest method which is known for the water splitting. Here we use the actually direct current to separate water into hydrogen and oxygen. And here the anodic and the cathodic reaction can occur. At cathode, the hydrogen evaluation reaction occur, and the OER, oxygen evaluation reaction occur at anode. These are the half cell reactions. And the difference between the electrocatalysis and the photoelectrocatalysis is that actually there are two differences. First, we use the light source, and the second, the cell setup is different. The rest is same in both the phenomena. We do have actually this setup also here in our research lab, and we have actually recently published some good papers based on the graphitic carbon nitride and the graphitic carbon nitride based heterostructure. So we have actually prepared the graphitic carbon nitride nanosheets because these are considered as the ideal candidates for photocatalytic water splitting because of the excellent band alignment. And we have prepared these the nanosheets of the graphitic carbon nitride by accelerating the melamine, which actually forms bulk graphitic carbon nitride at 520 degree centigrade temperature. And if we exfoliate the bulk graphitic carbon nitride in sulfuric acid or the HCl, then it produces very beautiful honeycomb, highly porous structure of the nanosheets. And these are the detailed SEM and the TM electron microscopic studies which show the very beautiful electron microscopic images which show that the buffet-like morphology of the bulk graphitic carbon nitride sheets, and these are the nanosheets of the graphitic carbon nitride, and the tilting of sheets could be seen when actually we do the exfoliation with the help of the SEM images. And before doing the water splitting studies, we do the primary investigations with the help of the BT surface area technique and the DRS study to calculate the optical band gap. So when actually we get the proper information about the surface area and the optical band gap, then we choose the particular light source to expose the solution with the help of the particular wavelength of the light. And here we do the two different set of the experiments. In one set, we do the hydrogen production with the help of the triethanolamine as the sacrificial agent, and in another set of the reaction, we take the sodium sulfide and the sodium sulfite as the sacrificial agent. And in both the phenomena, we have observed that the triethanolamine can produce the high amount of the hydrogen, which is around 470 micromole per hour, with an apparent quantum yield of the 12%. Whereas the mixture of sodium sulfide and sodium sulfite can produce 230 micromole per hour per gram hydrogen with an apparent quantum yield of around 7.3%. And both the results are much better than the bulk graphite carbon nitride sheets. And these are the detailed electrocatalytic properties. And here, this is the LSV plot for the HER reaction, and this is the LSV plot for the OER reaction. Both the plots show that the low onset potential, which shows the high HER current density in presence of the acidic media. And these are the Tefel slope, which gives the low value of the over potential of the graphite carbon nitride nanosheets in sulfuric acid, and its value was around 116 millivolt per DEC. So the low value of the Tefel slope shows the high HER activity of the graphite carbon nanosheets in acidic media. We have also actually calculated the intrinsic activity with the help of the TOF turnover frequency measurement. So with the help of all these measurements, we have actually we can conclude that the effective hydrogen evaluation reaction could occur with the help of the nanosheets of the graphite carbon nitride. Then we have actually used these graphite carbon nitride to make the heterostructures with other oxides. So in our one experiment, we have fabricated the heterostructures of the graphite carbon nitride nanosheets with copper ferrite nanoparticles. And this is the schematic procedure. First, we have prepared the graphite carbon nitride nanosheets and as prepared copper ferrite nanoparticles by using hydrothermal assembly. Then we actually mix both of them mechanically, and we form the heterostructures of the copper ferrite and graphite carbon nitride nanosheets. And we have actually published this paper in each applied material interface. And these are the primary investigations. Like we do the detailed X-ray diffraction analysis, which shows the formation of the different compositions of the copper ferrite and graphite carbon nitride nanosheets. We have prepared actually 10 weight percent loading, 20 weight percent loading, and 30 weight percent loading of copper ferrite over the graphite carbon nitride nanosheets, and calculated their surface area parameters as well as the optical band gap. And these are the detailed electron microscopic investigations for the grain size, structure, morphology of these heterostructures. Now, coming to the photocatalytic water splitting phenomena for hydrogen production, and here you can see that actually here also we have actually made two different experiments. In one experiment, we have used sodium sulfide as sacrificial agent, and in another experiment, we use the TEOA, means triethanolamine, as the sacrificial agent. And we have actually found that the triethanolamine can produce the maximum, like 1 millimole per gram hydrogen when we use triethanolamine as the sacrificial agent with an apparent quantum yield of 28%. And we have observed that the 28% copper ferrite loading over the graphite carbon nitride can produce the effective result. And after this loading, actually the hydrogen production reduces because of the reduction in the light absorption due to the and hence actually there is a decrease in the formation of the electron hole pair. And the best results we obtained using triethanolamine as a sacrificial agent because the nature of the sacrificial agent and the catalyst are actually non-polar, which can actually improve the interaction and wettability of the catalyst surface. And these are the actually charge transfer dynamics. It shows that this is the EIS plot. Here you can see the lower charge transfer resistance of the copper ferrite graphite carbon nitride nanosheets, which can actually leads to enhanced interfacial charge transfer. And these are the more Schottky plots for the pure graphite carbon nitride, and this is for pure copper ferrite nanoparticles, and this is for the heterostructure. If you see the more Schottky plot, then here you can see the positive slope which shows the n-type semiconductivity in graphite carbon nitride, and here this is the negative slope, which shows the p-type semiconductivity in copper ferrite. And in the heterostructure, not shortly plot, both positive and negative plots could be seen, which shows the p-n heterojunction formation of the copper ferrite graphite carbon nitride nanosheets. And actually, when we do the detailed PL photoluminescence study, it shows that the intensity, PL intensity, is decreasing when we actually make the heterostructure formation, which shows the stability in the electron hole pair recombination. And these are the band structure diagram. This is the band structure of the copper ferrite, and this is for the graphite carbon nitride before actually making the heterostructure. But when we start making the heterostructure formation, then the Fermi level alignment occurs. During this alignment, actually, the electrons of the conduction band which are present in the conduction band of the copper ferrite may tunnel from here to the conduction band of the graphite carbon nitride, whereas the holes in the valence band of the graphite carbon nitride tunnel from here to the valence band of the copper ferrite. So it forms the type 2 heterojunction that we have reported in the literature. Then these are the electrochemical studies, OER plot and the HER plots, which show the improved current density and the lower over potential, which show the 28% heterostructure can actually produce the effective water splitting reaction, and the maximum Faraday efficiency could be obtained, which was around 95% for 28% copper ferrite and graphite carbon nitride. Dr. Sir, we have some time.
Dr. Sir, you have only.
How much time I am having?
Yeah, you have 2 minutes, please.
Oh, 2 minutes. So I will try to compile. Right. So then we have actually made the heterostructure of the copper oxide with graphite carbon nitride, and these are the primary investigations. I will not go into the details. Then we do the theoretical study for getting the accurate information about the band structure. Then these are the electron microscopic studies. Yeah, this is the interesting slide. Here actually the 3 mole % loading of copper oxide over graphite carbon nitride can generate the high amount of the hydrogen, which was around 1 millimole per hour, whereas it can produce the total hydrogen production, which was 3.5 millimole after 5 hours, and its apparent quantum it was increased from 10 to 18%. So we are actually first in the literature who have reported the apparent quantum yield of this material is so high. Actually, these are the electrochemical study, and we have shown the possibility. Actually, the iridium oxide is the commercially available material for the OER and the HER reaction, effective OER HER reaction, and we have shown that the copper oxide and graphite carbon nitride heterostructure is the best replacement, because actually when you see these results, electrochemical LSP and the for HER and the OER plots, and as well as the TEFL slope, these studies show that the graphite carbon nitride copper oxide heterostructure is an impressive electrocatalyst for actually replacing the iridium oxide that is commercially available. And this is the ternary heterostructure. Actually, we have prepared the MOS2 BN TiO2 ternary heterostructure by using X-ray diffraction. We have investigated in detail. Then these are the electron microscopic studies, which here we also showing the optical band gap tuning of the ternary heterostructure formation, and then we do the DFT investigation. Because of shortage of time, I cannot actually explain this slide. And these are the actually detailed water splitting phenomena. We actually produce hydrogen by taking their monophasic structure, binary, as well as the ternary heterostructure, and we have found that the ternary heterostructure formation means 2.5 weight % loading of MOS2 boron nitride over TiO2 can generate around 2.7 millimole per hour per gram hydrogen production. And these are the actually surface area and other investigations also. And here actually we have explained why the 2.5 weight % loading over the TiO2 can generate maximum hydrogen production. So we have actually correlated with the help of the band energy diagram that the electron hole pair actually structure is more stable for 2.5 weight % loading over the heterostructure formation. These are the detailed electrochemical investigation. and the electrochemical active surface area, the high value of electrochemical active surface area, and low Tefel slope for 2.58% MOS2 boron nitride OTIO2 heterostructure can actually show the significant electrochemical results for water splitting. And these are the photoelectrochemical investigations which show that the photoelectrochemical water splitting is best or better than the normal electrochemical water splitting. And I will not show, actually these are the simple metal dot SNO2 heterostructures. So now I am skipping these slides because actually there is no time. Yeah, now coming to the conclusion, actually we have actually obtained the adequate apparent quantum yield of 12% and high periodic efficiency of 98% for graphitic carbon nitride, and we have shown that this material is a prominent metal free semiconductor for producing hydrogen gas. And 28% copper ferrite loading over the graphitic carbon nitride can produce significant hydrogen with an apparent quantum yield of 25% and the enhanced Faradic efficiency of the 94%. We have also shown that the copper oxide graphitic carbon nitride heterostructure is a best replacement for the commercially available iridium oxide, and it can produce a very effective hydrogen production within 18% of the apparent quantum yield. And the effective band alignment of the ternary heterostructures of MOS2 boron nitride and TiO2 to be seen, and the 2.58% loading of MOS2 boron nitride over TiO2 can produce the effective and the significant photocatalytic response for hydrogen production as well as high apparent quantum yield for the photochemical reactions. So I would like to thank all my collaborators, my students, the funding agencies, and my university for this kind of work. And I'm also thankful to the organizers for inviting me. And I'm sorry for actually making the trouble, because actually the program was not in my knowledge due to actually the all mails went to my spam. But I'm thankful to Professor Anurag for reminding me, and I was ready for that. Thank you all for your kind attention. Thank you.
Thank you, Professor Tokir Ahmed, for the nice talk. And now talk is open for question. 1 or 2 questions. Yes, yes. You can come here.
If there is a question, you can write also in the chat box.
Yeah, you can ask here.
Hello. Good evening, sir. Sir,
Good evening.
What is the difference between C3N4 and GC3N4?
C3N4 and GC3N4.
Yes, sir. Yes, sir.
Actually, this is the same material. It is called as the graphitic carbon nitride. Actually, this is made from the melamine, which is the derivative of the graphite. Actually, so both are same material. Generally, it is denoted as GC3N4.
Yes, sir. Yes, sir. Generally, we show in literatures GC3N4 and in some literatures C3N4.
Actually, it depends on the person to person. Sometimes they write actually C3N4. I generally write GC3N4.
Okay. Okay. Thank you, sir. Thank
So
you.
GC3N4 stands for the graphitic carbon nitride. This is the full name. Actually.
Okay. Okay, sir. Thank you.
So once again, thank you, Professor Tokir.
Thank you so much, Professor Rajesh.
So there is no more question. So now stopping here. So now we are moving the next oral presentation online. Dr. Sahab, stop sharing, please. Yeah. So next talk is Nsut Gupta. He's online? Okay. So how to proceed it? Oh, okay, okay.
Am I audible?
Yes.
Can I start now?
Now, yes, you can start.
Okay. So I'm going to slide some more. Just let me know anybody if it is already visual to you. Is the presentation mode is visual to you? Hello, am I audible?
Yes, yes.
And can you see my presentation?
Yes, you can go on the full screen mode.
It is already in full screen mode. So that's why I just want to get it confirmed from your side. If first slide is visual, then absolutely fine.
Yes.
Is my first slide visual? Can anybody confirm it?
Oh, sorry. Yes.
Hello?
Yes, now you can start. Hello? Hello?
Is my first slide visual?
Yes, yes.
Okay, thank you very much, the organization team, for calling me here for my work. And good afternoon to Indian participant, and good morning and good evening as per your global presence.
Yes, so now you have 10 minutes.
Yeah, of course, it has already started.
Yeah, okay.
So, my name is Nsut. I am from Maya College of Science and Commerce as well as GG Ruparel College, Mumbai. And today I am just going to discuss something about tellurium dope PN device fabrication by thermal diffusion on GSP VDS substrate. And right now what you are seeing here is a group called as Central Research Laboratory at GG Ruparel College. It consists of Jain College, Ruparel College, and fine, there are four or five colleges. So I am directly coming to the work which I need to present here. We actually grow third semiconducting element through semiconducting compound through vertical directional certification VDS technique. So this work presently focus on gallium antimonide, which is a direct band gap semiconductor having 0.726 electron volt room temperature band gap that corresponds to NIR of 1.7 micrometer. And what we are going to do is we are having GSB, INSB, and different third semiconductors, and then we dope them accordingly. Depending upon their requirement of P or N type. Focusing again here to GSB.
Excuse
it
me.
is P type. Hello? Yes?
Your slide is not moving.
Yeah, I am not moving it either.
Okay. So now you are on first slide.
I am on the first slide only.
Okay.
But that is the problem. No, actually, I have gone through. So in this mode, I think it is far more visual. I can continue here also. Now it is moving. Fine. Fine. No problem. So I will continue here only. I think now it is moving. So gallium antimonide, we are very much focused with it. It's a P-type direct band gap semiconductor. It is always P-type. There are some reports that under extreme pressure it may reverse its polarity, but we are having it P-type, so we need to dope it with N-type semiconductor so that we can make it as a junction, which we are looking for for IR detection in fact. So this substrate, what we call a GSP VDS substrate, I will go it very fast, is the substrate grown by vertical directional solidification. It's a very smart technique so that we can grow crystals without a seed. We don't give any seed, and without contact to the ampoule wall, without coating, and without external pressure. But that is not the beauty of this thing. The beauty is the crystal grown by VDS is as good as the crystal grown in microgravity conditions. It has been already reported multiple times starting from 2005 onwards. So the crystals we are having, the substrates we are having of third semiconductor, GSP, NSPN, INSP, INSPPI, etc. So out of that, GSP is present work. So this GSP will be converted by doping of N-type substance into a PN junction. Before that, its resistivity was measured at 3.6 into 10⁻² ohm centimeter. Of course, Yeah. So we in our lab, Central Research Laboratory, we dope our junctions through three methods: ion implantation, diffusion, and magnetic sputtering, of course. So out of the three, ion implantation we do at IUAC, Delhi, magnetic sputtering at our lab only, and diffusion at our lab only. So before this work is very much focused on diffusion, as its title says. But before that, our substrate were irradiated by 200 keV lithium ions with the fluence very close to 10 to the 15 ions per centimeter square at IUAC. It was used only to make trap centers and reducing the carrier concentration. Actually, the carrier concentration is reduced by one factor. So now to use our substrate and dope them by diffusion. The crystals are well cut. The size is around half centimeter square because they are little irregular samples. And then these samples, they are masked with aluminum foil. Why I am saying aluminum? Because the even for the radiation, uh, when we go for when we go to IUSC for the radiation part, it is penetrated to almost 1 by 20th of the thickness of our aluminum foil. So we can use it as a good masking, masking agent, and we mask it, and then the remaining exposed part is uh, either implanted or diffused. Yeah, this is our sample size. So in this sample, half part is masked after Li irradiation. So this whole body is Li irradiated. The concentration is reduced by one factor, and then half mask and rest part is subjected for the diffusion or implantation as the case. In this case, it is diffusion. So diffuse GSP substrate, the first that is electrically characterized, then doping through diffusion, then it's annealing, then again post annealing electrical characterization. In fact, we do the characterization before annealing also. So for this thing, GSP was doped by tellurium. Tellurium is a good fixed element, and it's very good N type for our GSP substrate. It is S-grown substrate, needless to say, but ohmic. And when we diffuse it, it is little rectifying. But since it is equally rectifying for either vising, right now it seems to be no direct use. What we are going to do? We anneal it. So annealing makes interesting difference. On right hand side, we see on the forward wise, annealing is making quite difference for 3.5 volt. So in simple words, if we talk in terms of p-n junction, we directly jump to ideality factor. And when we go for the ideality factor confirmation, we see that, okay, that's the measurement type, everybody do with the same thing. So ideally factor, what we were having 4.6 in the case where it was not annealed, which jumped to, it is reduced by a factor of, half, almost, more than that. So diffuse annealed ideally factor is 2. And 2 is very much within the required range. Fine. So this is something we are looking for. So this junction which were constructed after Li diffusion and after Li irradiation and Te diffusion gives us the ideality factor 2. So that is the whole work what I want to discuss over here, some references, and then this is actually where we diffuse the junction. Thank you very much, everyone. Am I connected? Am I connected?
Yes. So it's over?
Of course, over. Ideally, my slides are not running. Nobody reported it. So last slide is visualized.
What should I do? Yeah.
So this part, which is most important, ideally factor I mean, reduction in additive factor was not visible.
Now it is visible.
Now it is visible. Okay. So I will just repeat in 1 minute the result part. On the very first small curve we are seeing is a straight line for ohmic region. As grown, GSV 35 semiconductor Y VDS process, and on right hand side we are having just diffuse. Of course, diffuse after Li irradiation, it is diffuse, followed by annealing. So annealing is making a significant difference in forward Y. In reverse Y it is there, but when we see the activation ratio, we are more interested that additive factor should be reduced, and it is reduced from 4.6 pre-annealed to 2 after annealing. Needless to say, in both the cases, it is Li irradiated first.
So thank you, Anshul. So now paper is open for question. Any question? So there is no more question. Thank you, Anshul.
Thank you very much. Thank you, everyone.
So in this session, next presentation is Priyanka Maurya.
Yes, sir.
So Priyanka, you have 8 minutes plus 2 minutes
Yes, sir.
for question. So total
Okay,
10
sir.
minutes.
My slides are visible, sir?
Yes.
Okay. Good afternoon. Good afternoon, everyone. Myself, Priyanka Maurya, a research scholar in the Department of Physics, MNIT Allahabad, Prayagraj. I am working with Professor S.N. Pandey. The title of my presentation is Silar Synthesized Binder-Free Aluminum Oxyhydroxide Thin Film as Supercapacitive Electrode. So, yeah, this is the outline of my presentation, which includes motivation, introduction, synthesis, characterization, electrochemical analysis, results, and conclusion part. Now comes to motivation part. There are 3 E's, namely energy, environment, and economy, which are the primary issues and concern with the human development. The environment-friendly energy can be divided into 3 parts. First one is its harvesting from renewable energy sources. Second, its conversion, and third one is storage. Among all these 3 parts, storage is an essential part. The battery and capacitor are the main storage devices. A battery has high energy density but low power density. On the other hand, a capacitor has high power density and low energy density. So we need some alternative which has the positive characteristics of both battery and capacitor. In the recent years, the supercapacitor fills the gap between the battery and capacitor due to its high energy density, power density, and also it has high cyclic stability. Introduction part. Energy sources are divided into 2 parts, non-renewable and renewable. Coal, natural gases, fissile fuel, nuclear energy are the example of non-renewable energy sources. But the problem with non-renewable energy sources are that they are limited. And next is renewable energy. Solar energy, hydrothermal energy, wind energy, biomass energy are the example of renewable energy sources. But problem is that due to their intermittent production of electricity and irregular use of electricity during a day, the efficient and reliable energy storage system are required. As supercapacitor has high energy density, power density, stability, so it is best energy storage system. Now, what is the difference between supercapacitor? How it is different from capacitor? Supercapacitor means super in energy density, super in power density, and super in its capacity. Features of supercapacitor: it has wide working temperature, fast charge discharge, eco-friendly, it has long cycle life, it is cost effective, and excellent power density. Now, classification of supercapacitor. Depending upon the charge storage mechanism, Either it is ferritic or non-ferritic supercapacitors are broadly classified into three parts. First one is electric double layer capacitor, second pseudo capacitive electrode material, third is battery type. Activated carbon graphene carbon nanotube shows EDLC type behavior, while conducting polymer metal oxide hydroxide shows ferritic behavior. Methodology. SILAR method is used for the preparation of thin film electrode. SILAR stands for successive ionic layer absorption and reaction technique. The reason for choosing this technique is that it does not require any high quality target or substrate. It works at room temperature. This is cost effective and less time consuming method. There is no need of any vacuum. And this slide shows the deposition of aluminum oxyhydroxide thin film by SILAR method. This is our stainless steel substrate. We dip into aluminum chloride solution first, where aluminum 3+ ion get absorbed, and we dip it here for 30 seconds. Then we dip it into DI water for 10 seconds, where loosely bound ions get unabsorbed. Then we dip it into sodium hydroxide solution, where OH ion react with pre-absorbed aluminum 3+ ion. And then we again rinse it with DI water so that loosely bound ions get removed. Thus, this completes one SILAR cycle. According to our requirement, we repeat this process so many times. Here, I prepared 10 and 20 SILAR cycle thin film for our application purpose. This is the characterization part. Figure 1.2a shows the XRD of the prepared sample. The obtained peaks are well matched with JCPDS card number 832384 and shows the orthorhombic phase of the prepared sample. Second is figure B represent the FTIR analysis. The band at 553 centimeter inverse and 1019 centimeter inverse shows the vibration of aluminum and oxygen. And bands from 1200 to 1800 centimeter inverse comes due to carbon double bond oxygen, carbon double bond carbon, etc. due to the impurity of environmentally present carbon. And the bands at from 3300 to 3800 arises due to the vibration of OH ion. Now, application part, electrochemical analysis. Figure 1.3 shows the CV curve for 10 and 20 cycle. From CV curve, we observe that 20 cycle has large area. High the area, high the specific capacity. Figure 1.3b show the GCD, galvanometric charge discharge curve. High the discharging time, high the specific capacity. And from A and B, we observe that 20 is the best. As in A, 20 has highest area, and in B, 20 has high discharging time. This slide shows the CV curve of 10 and 20 SILAR cycle aluminum oxyhydroxide sample at various scan rate. And this is the GCD curve of 10 and 20 SILAR cycle sample at different current rates. Now, result. The specific capacity is calculated by the formula equal to area under the curve divided by mass into scan rate. And the results are tabulated as from which 20 cycle has highest specific capacity of 1148 coulomb per gram is obtained at 5 millivolt scan rate. Now, conclusion. Hence, thus, aluminum hydroxide thin film was successfully synthesized by SILAR method. The XRD and FTIR characterization confirms the formation of fin by providing structural and bond analysis. After that, we analyze the sample by in 1 mole in Na2SO4 electrolyte for electrochemical analysis.